Hello and welcome to this course. Almost everyone has used a database, and more likely, information about us is probably present in many databases all over the world. But who understands what a database is and how important databases are to global industry, government, and organizations? A very straightforward description of a database is that it is a form of electronic storage in which data is held. Of course, that explanation does not even come close to explaining the impact of database technology. To give an idea of databases in a real-world context, let's briefly describe some typical use cases. For example, your bank uses a database to store data for customers, bank accounts, and transactions. A hospital stores patient data, staff data, laboratory data, and more. And an online store retains your profile information along with your shopping history and accounting transactions. Many of these services have access to a diverse range of data. They collect and store other items such as your location, how long you spend on their platform, and friends you connected with, alongside many more facts. Such online services and social media platforms generate enormous amounts of data due to their large user base and constant user activity. And with the Internet of Things, or IoT, many extra devices are now connected to the Internet. These continual streams of data have led to a revolution in database technology to accommodate the volume, variety, and complexity of what has become known as big data. Whatever the source of the data, a database will typically carry out the following actions, all of which a developer such as yourself must be familiar with. Store the data, form connections or relationships between segmented areas of the data, filter the data to show relevant records, search data to return matching records, and have functions to allow the data to be updated, changed, and deleted as required. Don't worry if you don't fully understand all these terms. For now, you're just receiving a brief introduction to databases and data. During the course, you'll explore these concepts in more detail alongside the many other tasks that form the duties of a back-end developer. You'll learn about the concepts of data and databases, how data is related in a database, and different database structures and their uses, how to perform, create, read, update, and delete operations, how to use SQL operators to sort and filter data, what database normalization is, and how to normalize a database. You'll also get to build a fully operational database, and you'll also install and set up software called XAMPP on your computer to help progress your local and remote database learning. There are many videos in your course that will gradually guide you towards that goal. Watch, pause, rewind, and rewatch the videos until you're confident in your skills. Then consolidate your knowledge by consulting the course readings and put your skills into practice during the course exercises. Along the way, you'll encounter several knowledge quizzes where you can self-check your progress. And you're not alone in considering a career as a back-end developer, which is why you'll also work with course discussion prompts that enable you to connect with your classmates. It's a great way to share knowledge, discuss difficulties, and make new friends. To be successful in this course, it is helpful to commit to a regular and disciplined approach to learning. You need to be serious about your study and, if possible, map out a study schedule with dates and times that you can devote to attending the course. It's an online, self-paced course, but it does help to think of your study in terms of regular attendance at a learning institute. In summary, this course provides you with a complete introduction to databases and is part of a program of courses that lead you toward a career in back-end development.
I really like this idea that in the end, we're all solving human problems through technology. And we're not, as a software engineer, my role is not to simply develop technological solutions. They need to have this human outcome. I'm Daniel Bloomfield-Ramagem. I'm a software engineer for Meta. I joined the company in 2017, and I work out of our Washington, D.C. office. I immediately think of my mother's recipe book, which is a spiral notebook. So she keeps her recipes in a spiral notebook. Every page has a number, and she keeps kind of an index at the beginning of that notebook so she can easily find the recipe. Well, that's a database. So, my mom is a database engineer, perhaps, or not engineer, but certainly she relies and has created her databases. So I like that fun kind of example because it shows the range of things that are possible once you store data in a structured way that can be easily retrieved. And so it's the recipe book, but it's also, the picture I just shared on Facebook that now my friends get to see anywhere they are in the world so quickly. All that is powered by a lot of infrastructure, databases at the core. I think data is at the heart of every application. And so learning to create an effective data layer that can provide the user with quick responses, accurate responses, and results is really critical. And as a database engineer in particular, I think you are involved in such a critical component of building applications, and you have such a large influence in everything else that follows from the data. So that includes the user interface. It includes the clients, the APIs, like all of that gets influenced by how the data layer gets modeled, stored, and all the characteristics of being able to retrieve that data effectively and making it the consumption of that information easy for the rest of the tech stack. So you have a really large influence, and I hope you walk away knowing that you have this very large influence on the development of applications. So technical skills I use on a daily basis. Certainly I code, and when I say code, I mean not only I program using kind of a standard programming languages for web, but I also work in the database space by creating the pipelines that produce, that extract, transform, and load a lot of the data that makes its way into the applications that we develop. The soft skills I use on a daily basis certainly include a lot of communication and organization. It's easy you come out of school and you're so excited about the coding, the technical skills you've learned, and those are obviously very, very important. But I thought code was king. I'm here to program. And I expect people to understand the output of what I'm making. And I learned that is insufficient. And I saw great examples of people who were doing great technically, but they were excelling furthermore on just being able to explain what they were doing, not only to the team internally, but to the people who are going to maybe use those features in the tool set. The perfect is the enemy of the good. Particularly, I think with database development, it's easy to overcomplicate solutions, and especially when you're doing data modeling and data storage. You want to cover every possible variation of data, every different use case, edge case for using that data. And that can lead you down the path of creating very complex data schemas that become hard to maintain, can be not well performant. So you need to iterate on your work. For databases, I would say, try to focus on the here and now needs of data. Be especially mindful of these perceived needs for massive data scalability, which may, again, lead you to overcomplicate your solution when in fact you might need something much smaller scale, at least to kick off and get better understanding of what the feature and the data requirements truly are. So start small, iterate frequently. Write more often. And I know usually when you think of engineers or database programmers, you think the output of your work is, it's the program, it's the code, it's the SQL queries. And yes, it is, but that alone I think is insufficient. So complement that with writing. Now, what are you going to write about? Well, certainly there's documentation that goes along with your code. I have a good colleague at Meta that always tells me when I said I'm done with something, he looks at me and says, "Are you done?" And I said, the first time he said it, I was like, "Yes, I'm done." And he followed up with, is your documentation ready? Is your code checked in the right places? Is the wiki page updated? Did you write a post about this? And so he emphasized the importance of code is the 80%, 20% is that additional communication that's needed. So I would say write more often. Don't be afraid to write imperfectly. Write something, put something out there, whether it's sharing the status of something that you're doing, whether it's just enhancing documentation for something that you're working on. Get into the habit of writing more often. Try to take what you're learning and connect it to something practical that you can see a use for. Whether it's learning about databases and thinking about a recipe book that your mother or father has in a spiral notebook, or maybe baseball cards that you tracked as a child, or comic books that you tracked as a child. Try to think of ways to apply what you're learning technically to these real life problems. They can be small problems like finding the recipes at the right time, but they can be, of course, bigger, more perhaps interesting problems around just technical and digital communication between people.
We all use data and databases in our daily online lives. For example, uploading photos to our social media feeds, downloading files at work, and playing games online are all examples of database usage. But what exactly is data, and how does it interact with a database? If you're struggling to answer these questions, don't worry. By the end of this video, you'll be able to describe what a database is at a conceptual level, identify real-world examples of the use of databases, and demonstrate an understanding of how data is organized in a database. So, let's return to the first of our questions. What is data? In basic terms, data is facts and figures about, well, anything. For example, if data were collected on a person, then that data might include their name, age, email, and date of birth. Or the data could be facts and figures related to an online purchase. This could be the order number, description, order quantity and date, and even the customer's email. Data is crucial for individuals as well as organizations. But where is all this data stored? In our digital world, data is no longer stored in manual files. Instead, developers use something called databases. A database is a form of electronic storage in which data is organized systematically. It stores and manipulates data electronically to make it more manageable, efficient, and secure. There are many real-world examples of where databases are used. For example, a bank can use a database to store data for its customers, bank accounts, and transactions. And a hospital uses a database to store patient data, staff data, laboratory data, and much more. At this point, you might be asking yourself, but what does a database actually look like? Well, a database looks like data organized systematically, and this organization typically looks like a spreadsheet or a table. What exactly does the term systematic mean? All data contains elements or features and attributes by which they can be identified. For example, a person can be identified by attributes like their age, height, or hair color, and this data is separated and stored in what's known as entities that represent those elements. As you just learned, an entity is like a table. It contains rows and columns that store data relating to a specific element. In other words, these are relational elements. They're related to one another. These entities could be physical representations, like an employee, a customer, or a product, or they could be conceptual, like an order, an invoice, or quotation. Entities then store data in a table-like format against the attributes or features related to the element. For example, an online store could hold customers' data in a customer entity containing specific attributes relating to the customer. These attributes could include first name, last name, date of birth, and email. And they could also have product data stored in a product entity against attributes like product code, description, price, and availability. In the relational database world, these entities are known as relations or tables. The attributes become the columns of the table, and each table row represents an instance of that entity. As an example, let's take the entities from the online store example that you just explored. These two examples could be combined into a list of orders the store received from its customers. Within a database, this data could be rendered as an order table or entity, and the data could be organized into rows that contain a unique order number, the name of the customer who placed the order, the product that they ordered, and the price of that product. There are many ways to organize data in a database. Relational databases aren't the only kind of databases that you'll encounter. As a database engineer, you'll work with many different types of databases. Here's a few common examples of other types of databases. An object-oriented database is where data is stored in the form of objects instead of tables or relations. An example of this kind of database could be an online bookstore. The store's database could render authors, customers, books, and publishers as classes, like sets or categories. The objects, or instances of these classes, would then hold the actual data. Graph databases store data in the form of nodes. In this case, entities like customers, orders, and products are represented as nodes. The relationships between them are represented as edges. And finally, there's document databases where data is stored as JSON, or JavaScript Object Notation objects. The data is organized into collections like tables. Within each collection are documents written in JSON that record data. So in this example, customer documents are held in a customer collection, while order and product documents are stored in the order and product collections. But where are the databases themselves stored? A database can be hosted on a dedicated machine within the premises of an organization, or it could be hosted on the cloud. Cloud databases are currently a more popular choice. This is because they allow you to store, manage, and retrieve data through a cloud platform and access data through the internet. And they all provide a lower cost option for data management than other similar options. You should now understand the concept of a database. You should also be able to identify examples of databases and demonstrate how data is organized within a database. Great start. You'll be storing and managing data in no time. Picture yourself in the following scenario. You're managing the database of a large online store. Your database must be able to retrieve a customer's details from one table and then find the order recorded against another table. So how does the database establish a relationship between these pieces of data? Over the next few minutes, you'll explore this process, and by the end of this video, you'll be able to explain why data in a database should be related and identify an instance of related data in a database. Data stored in a database cannot exist in isolation. It must have a relationship with other data so that it can be processed into meaningful information. So how do you make sure that all the data in your database is related? Let's explore how data is related by using the online store as our example. In the database of your online store, you could have an order table and a customer table. To locate the details of a customer's order, you would check the order number against the customer ID. In other words, the database establishes a link between the data and the tables. Let's look at the customer table in more detail. In this table, the columns are customer ID, first name, last name, and email. In relational database terms, these are fields. Then there are several rows which contain data for each of these fields. In relational databases, they are known as records of the table. So, all these fields and rows work together to store information on the customer, also known as the entity. Every row and record in the customer table is an instance of the customer entity. For example, Sarah Hogan, who has a customer ID of C1, is one customer instance. And Katrina Langley, who has a customer ID of C4, is another customer instance. What's most important is that each of these customer instances, or records, must be uniquely identifiable. But what if two or more customers share similar info, like the same first name or last name? To avoid this confusion within the database, you can use a field that contains only unique values like the customer ID. This is called a primary key field. It contains unique values that cannot be replicated elsewhere in the table. So even if two customers share the same name, they'll still have separate customer IDs. This means that your database can determine which customer is the required one. Let's look at the order table next. Just like the customer table, the order table also has fields and records. And in this table, the primary key field is the order ID. But there's also a field named customer ID with the exact same data as the customer data. So what is the purpose of the customer ID in this table? The customer ID is there to help identify who it is that placed the order. So by adding the customer ID field to the order table, a relationship is established between the customer table and the order table. And because of this relationship, you can pull data in a meaningful way from both tables. The customer ID field in the order table is known as the foreign key field. A foreign key is a field in one table that connects to the primary key field in the original table, which in this case is the customer table. So the customer ID is the primary key of the customer table, but it becomes the foreign key in the order table. This way, the relationship is established and the data in these two tables are related. You should now be able to explain the relationships between data in a database and identify instances of related data. Great work. You've probably heard of terms like big data and cloud databases. Maybe you've even encountered them in this course. But do you know what they mean? In this video, you'll discover more about these terms and you'll be able to identify different types of databases and explain how databases have evolved in response to new trends like big data. Databases have been around for a long time and have been influenced by many different trends, but they've undergone a huge change in recent decades. Thanks to the growth of the internet, they now must be able to store ever-increasing amounts of unstructured data. However, this poses difficulties, as they mostly store structured data. Let's briefly look at some of the different types of databases and how they've been affected by this trend. Relational databases have limitations when it comes to storing data because they mostly store structured data. Yet databases are now required to store more and more unstructured data. So the trend in recent years has been to rely on NoSQL databases instead. NoSQL databases are a type of database that store data in a variety of different formats. Essentially, they provide databases with a flexible structure. This makes scaling easy by facilitating a change to the database structure itself, without the need for complex data models. NoSQL databases are used by social media platforms, the Internet of Things, artificial intelligence, and other applications that generate massive amounts of unstructured data. Types of NoSQL databases include document databases, key-value databases, and graph databases. Now that you're familiar with different types of databases, let's take a closer look at big data and cloud databases. Essentially, these terms are used to describe a recent change in our approach to data and databases. Let's start with a look at big data. Big data is complex data that can increase in volume with time. In other words, it's data that can grow exponentially with time. But where does this kind of complex data come from? Social media platforms, online shopping sites, and other services generate massive amounts of data every second of the day as they capture the actions of billions of users around the world. And with the Internet of Things, or IoT, more and more devices are connected to the Internet, generating even more and more data. This is how complex data, or big data, is created. All this data is highly unstructured or semi-structured. Traditional database systems could deal with structured data using tables, records, and relationships. But big data is a whole new challenge. Big data is a combination of structured, semi-structured, and unstructured data collected from many different sources. And it adds more power to data because it can address complex business problems that traditionally structured data can't handle. Finally, big data helps to provide unique insights that can help to improve decision-making, so it's highly valued across many industries. For example, the manufacturing sector processes big data to predict equipment failure by evaluating the current state of machinery, assess production processes by monitoring the production line, respond to customer feedback proactively, and anticipate future demands by monitoring current sales. Retail processes big data to anticipate customer demand, improve customer experience, analyze customer behavior and spending patterns, and identify pricing improvement opportunities. And the telecommunications sector utilizes big data analytics and network usage analytics to plan for infrastructure investments, design new services that meet customer demands, analyze service quality data to predict customer satisfaction, and plan for customer retention mechanisms. Now that you're familiar with big data and how it helps to power businesses, let's move on to another trend in databases: the use of cloud databases. Organizations are moving to the cloud to free themselves from the difficulties of dealing with the infrastructure of physical servers, like maintenance and storage costs. Some examples of cloud storage services include Dropbox and iCloud. With these cloud storage services, it's possible to store documents and other data on the cloud, a much more affordable solution. Another trend in databases is business intelligence, or BI. Traditionally, databases were just a means of storing data, but organizations now utilize their data with business intelligence-related technologies and strategies. With these technologies, organizations can analyze their data and extract valuable information to help them to make informed business decisions. New trends are constantly emerging in database technology, and they'll keep advancing with time. But for now, these are a few of the leading trends that you should be aware of. At this stage in the course, you're probably familiar with the basics of databases and how they store and manage data. But it's also important that you know how to interact with databases in order to work with data. As a data engineer, you can interact with databases using structured query language, or as it's more commonly known, SQL, also pronounced as SQL. Over the next few minutes, you'll learn how to explain what SQL is and outline the role of SQL in databases. So what sort of interactions do database engineers need to establish with databases? Some of the operations you could carry out in the data might require you to create, read, update, and delete data. These operations are also known as CRUD operations. You might already be familiar with some of these operations. If not, don't worry. They'll be covered in depth at later stages in this course. Let's find out more about SQL. SQL is a standard language that can be used with all databases. It's particularly useful when working with relational databases, which require a language that can interact with structured data. Some examples of relational databases that SQL can interact with include MySQL, PostgreSQL, Oracle, and Microsoft SQL Server. The next question this raises is, how does a database interpret or read and execute instructions given using SQL? A database interprets and makes sense of SQL instructions with the use of a database management system, or DBMS. As a web developer, you'll execute all SQL instructions on a database using a DBMS. The DBMS takes responsibility for transforming SQL instructions into a form that's understood by the underlying database. This was just a very quick introduction to SQL. At this early stage, you should be able to explain what SQL is and explain the role of SQL in databases. In the upcoming videos, you'll learn more about SQL and develop a deeper understanding of the language. Imagine that you've just been hired to create a database for a college. First, you'd need to create tables to hold data in all aspects of the college. Then you'd need to insert data into these tables, and then modify this data whenever something changes. That's a lot of work, but it's all possible with the use of SQL and CRUD operations. Not familiar with these operations? No problem. Over the next few minutes, you'll learn how to explain the tasks that SQL syntax is used for when building a database, and demonstrate an understanding of the SQL subsets and sublanguages. So, let's return to our college database scenario. How can you possibly make all these changes in the database? Well, with the help of what web developers call CRUD operations. Performing CRUD operations is the most common task when working with a database. CRUD stands for create, read, update, and delete. Or in operational terms, create, add or insert data, read data, update existing data, and delete data. Alongside these operations, there are many other things that SQL can do. Depending on what SQL is used for, it can be divided into many subsections or sublanguages. These include DDL, or Data Definition Language, DML, also known as Data Manipulation Language, DQL, or Data Query Language, and DCL, also called Data Control Language. Let's take a closer look at these languages and their commands, starting with Data Definition Language, or DDL. DDL, as the name says, helps you define data in your database. But what does it mean to define data? Before you can store data in the database, you need to create the database and related objects like tables in which your data will be stored. For this, the DDL part of SQL has a command named create. Then you might need to modify already created database objects. For example, you might need to modify the structure of a table by adding a new column. You can perform this task with the DDL alter command. You can remove an object like a table from a database using the DDL drop command. Data Manipulation Language, or DML commands, are used to manipulate data in the database, like inserting, updating, or deleting data. Most CRUD operations fall under DML. To add data to a table, you can use the insert command. This command lets you specify the fields to add data to, along with the values to be inserted. If you need to edit data that's already inserted into a table, just deploy the update command. And you can specify data to be removed by using the delete command. So far, you've learned how to add database objects and manage data within them. So how do you read or retrieve that data? To read data stored in a database, you can use Data Query Language. DQL defines the select command to be able to retrieve data. Select lets you retrieve data from one or multiple tables, letting you specify the data fields that you want based on preferred filter criteria. And finally, you can also use DCL, or Data Control Language, to control access to the database. For example, using DCL commands, you control access to data stored in the database. Grant and revoke DDL commands are used to give users access privileges to data and to revert access privileges already given to users. You should now be familiar with how SQL acts as the interface between the database and its users. And you should also be able to identify SQL operations and sublanguages. Great work. By now, you're most likely familiar with the basics of databases, and you might even have come across some simple SQL syntax. But why do developers use SQL to interact with databases? SQL is a popular language choice for databases because of the many advantages that it offers. Now, over the next few minutes, you'll identify the advantages of SQL and demonstrate how the advantages of SQL assist with database tasks. SQL is the interface or bridge between a relational database and its users, and offers web developers a wide range of advantages. Let's look at a few of them. The biggest advantage of SQL is that it requires very little coding skills to use. It's just a set of keywords. There aren't many lines of code required to perform basic CRUD operations, or add, create, update, and delete tasks on the database. So it's a very developer or user-friendly language. SQL's interactivity makes it even more user-friendly because it lets developers write complex queries in a short space of time. So, if you need to work with relational databases for your next project, you just need to know what keywords to use and when. SQL is also a standard language that can be used with all relational databases, like MySQL. This also means that there's a lot of support and information available. So, SQL can run on any computer once you have database software installed. SQL is also a portable language. Once you write your code, it can then be used on any hardware and any operating system or platform, wherever you need. So if you write SQL code in a desktop and then move it to a production server environment, it will run the same in both locations. Also, SQL is a comprehensive language that covers all areas of database management and administration. For example, it allows you to create databases, insert, update, and delete data, retrieve and share data among multiple users, and manage database security. This is made possible through subsets of SQL, like DDL, or Data Definition Language, DML, also known as Data Manipulation Language, DQL, or Data Query Language, and DCL, also known as Data Control Language. And the final advantage of SQL is that it lets database users process large amounts of data quickly and efficiently. You now know that SQL is a simple, standard, portable, comprehensive, and efficient language that can be used to communicate and work with relational databases. You're well on your way to mastering SQL. Well done. As you might already know, you can interact with the database using SQL. But just like with other coding languages, you need experience with SQL syntax and its subsets before you can make use of it. Over the next few minutes, you'll learn how to create a database using the Data Definition Language, or DDL subset of SQL, utilize the Data Manipulation Language, also known as the DML subset, to populate and modify data in a database, and read and query data within databases using the Data Query Language, or DQL subset of SQL. In order to demonstrate SQL's syntax and its subsets, I'm going to show you the SQL commands that can be used to develop a database for a college. However, take note that the demonstration which follows will only briefly show each step in the process. You just need to develop a working familiarity with SQL for now. You'll explore the language and its subsets in much more detail later in this program. The first task is to create the database. To do this, I write a create statement using SQL's DDL subset. So, the syntax to create a database is create database, followed by the name of the database. I then place a semicolon at the end of the statement. Let's create a college database as an example using the syntax create database college. Once you've created a database, the next step is to create the tables. You can create tables using the create table syntax, followed by the table name. Just repeat these same steps for each new table you want to add to your database. I can use this syntax to create a student table in my college database. This table will hold information on each student. To create the table, I just write create table student. Now I need to populate the table with data. This is where I can use the Data Manipulation Language, or DML subset of SQL. To add table data, I use the insert into syntax. This inserts rows of data into a given table. I just type insert into, followed by the table name, and then a list of required columns or fields within a pair of parentheses. Then I add the values keyword and specify in order the values for each of the fields. As an example, let's add data to the student table in our college database. I'll use the student table I created earlier and add student data to it by specifying values for each of the following columns: ID, first name, last name, and date of birth, and then populate the table with the required data. But what if I need to update or modify data? For example, let's say I've input the wrong date of birth for a student. To change this data, I can use the update syntax, which is part of the DML subset of SQL. First, I add the update keyword, followed by the student table name. Then I use the set keyword, followed by columns and values I want to update, written as key value pairings. In this instance, it's the date of birth column and a new date of birth value. Finally, I add the where clause and a condition to filter the records I need. For example, to change the data for the student with the ID of 2, I can type where ID equal to 2. It's also possible to delete data from a table. Let's delete the table record for the student with the ID of 3 using the delete syntax. First, I type delete from, then the table name. This tells MySQL where the data must be deleted from. This is followed by the where clause and a condition such as ID equal to 3, which would remove all data on row 3 of the table. So I could instruct MySQL to remove the data of the student on row 3. Once I run the statement, the student's data is removed from my table. You're now familiar with how to add, update, or delete data in a database. But how would you read data stored in your database tables? That's where SQL's DQL, or data query language, comes in. The main syntax of DQL is select. As its name says, it's used to select data from the database. A select statement is written using the select keyword, followed by the columns that hold the data you required. You then write the from keyword, followed by the name of the table you want to select data from. As an example, you could use the select statement to query the student table to find the name of the student with an ID of 1. You would just need to add the where keyword, followed by the student's ID. This would then return the name of John Murphy. You're now familiar with the basics of SQL syntax and its subsets. Don't worry if you're still trying to figure out these subsets. You'll explore each of them in more depth later in this specialization, and you'll also get an opportunity to try them for yourself. At this stage of the course, you're probably familiar with the basics of how databases store and interact with data. But how do they store all this data and present it in a logical way? In the form of tables. By the end of this video, you'll be able to outline what a database table is at a conceptual level, and explain how data is structured in a database table. As you probably already know, the table is made up of rows and columns which hold data, and a table is stored in a database. In a database that holds multiple tables, these tables are known as relations, as they all relate to one another. In a more conceptual or logical sense, a table is also known as an entity. And in object-oriented databases, or OODB, an entity is an object that has attributes that are like columns or fields in a table. So in essence, a table, entity, and object all refer to the same concept. Within every table are columns, also sometimes called fields or attributes. Each column or field has a unique name and data type. For example, I have a table that contains data on employees in a company. The table organizes the data into columns such as ID and role, and each column can hold different types of data like numeric or string. A set of columns or fields form a row. In relational database terminology, a row is known as a record. So a record is a combination of columns or fields that contain data. In my employee table, for example, each row is a single employee record. Let's return to columns for a moment. As you now know, every column has a data type. The data type of a column defines what type of value a column can hold, like integer, character, date and time, and so on. It's up to the developer to decide the data type for each column. And it's also a guideline for SQL around what data type to expect in each column and how to interact with the underlying data stored physically. However, data types can vary depending on the database system. For example, you might have different types for MySQL, SQL Server, or Access. Always refer to the documentation of the relevant database system to check what data types it supports. Generally, all database systems support string data types for storing characters in strings of characters, numeric data types to store exact or whole numbers and approximate numbers, date and time data types to store information on date and time, and binary data types to store images, files, and other information. Another important concept related to tables is domains. A domain is the set of legal values that can be assigned to an attribute. Basically, this means making sure that the values a field can hold are well defined. For example, you can only place numbers in a numerical domain, and you can only place characters or strings of characters in a string domain. And each of these domains must include length, values, and other relevant rules that define its function. Each row or record in a table is also uniquely identified by what's known as a primary key. A column in the table that has unique values will become the primary key of the table. In the employee table, for example, the ID column is the primary key as each ID is unique. This is because the other columns could contain repeating values. For example, two employees may share the same name or role. It's also possible for a primary key to be a combination of columns if a single column alone doesn't possess unique values. You should now be familiar with what a database is and be able to explain how it is structured. You should also be able to explain key concepts such as columns, rows, and keys. Great work. At this stage of the course, you're probably familiar with the relational database model. But to fully understand how a relational database model works, you first need to understand how tables within a database are related. Essentially, relationships are established between tables with the use of keys. By the end of this video, you'll be able to identify the main keys used in tables in a relational database and explain the relationship between keys in a table. The relational database model is based on two main concepts: entities, which are defined as tables, and relations that connect to related tables. To realize how this model works, you need to understand the different key attributes that exist in the relational database. To demonstrate, let's use the example of a sports competition that uses three tables to keep track of the league: the league table, the teams table, and the points table. Each table has relevant columns, where each column represents an attribute of the table entity. The league table keeps track of each team's position in the league, their name, and the state they represent. The team's table tracks the team name, the team captain, and the team coach, and the points table records the team's position in the league, the team's name, and how many points the team has this season. Notice that the teams table includes team name, which also belongs to the league table. These attributes could be of a simple attribute type that can hold a single value. For example, in a table of staff members in a college, each staff name attribute has a single value in each row. Or they could also have a multi-value attribute that can have multiple values, like a list of subjects taught. However, multi-value attributes should be avoided in relational database design. You'll learn more about this concept later in the course. Let's use the example of the staff table to explore some examples of attribute keys. Let's begin with the key attribute. This is a value used to uniquely identify an individual record of data in a table. For example, in the staff table, the key attribute is staff ID. This attribute has unique value in each row of the table, so it's the perfect way to uniquely identify each record of data. In a relational database, there are a range of different types of key attributes. There's also the candidate key attribute. This is any attribute that contains a unique value in each row of the table. In the case of the staff table, both the staff ID and contact numbers are examples of candidate keys. Each has a new unique value in each row. The other columns can contain repeated information, so they're designated as non-key attributes. A composite key is a key that is composed of two or more attributes to form a unique value in each new row. In the staff table, an example of a composite key is a combination of the staff name and staff title, assuming that there isn't another instance of the same combination elsewhere in the table. A composite key is usually considered when a single attribute key can't be identified. A relational database must also contain a primary key, which you should already be familiar with. In the staff table, the staff ID is the primary key. An alternate key, also known as the secondary key, is a candidate key that was not selected to be the primary key. Just like a primary key, it's a column that contains a unique value in each field. For the staff table, the contact number is the secondary key on each row. And finally, there's the foreign key. The foreign key is an attribute in a table that references a unique key in another table. Typically, a foreign key references the primary key of another table. For example, the staff ID might also be a foreign key in one or more tables within the college database. The relationship between primary and foreign keys will be discussed in more detail at a later point in this course. You're now familiar with the different types of keys in a relational database. You've reached the end of this module on Introduction to Databases. In this module, you've discovered the basics of databases and data, received an intro to SQL, or structured query language, and explored the basic structure of a database. It's now time to recap the key points and concepts you learned and skills that you gained. You began the module with an introduction to databases and data. Following the completion of this first lesson, you can now provide an overview of what a database is at a conceptual level, outline real-world examples of database usage, and explain how data is organized within a database. You can now also explain the importance of related data within a database, identify an instance of related data within a database, and provide an overview of new trends in database applications. You're also able to identify different types of databases and provide a high-level overview of how databases have evolved. Following your exploration of databases and data, you were then introduced to SQL. This lesson focused on the basics of SQL, or structured query language. During this lesson, you learned how to outline the purposes of SQL and demonstrate an understanding of the role of SQL in databases. You can also identify the advantages of SQL, such as its low entry level, its wide range of applications, and its portability across operating systems. And you can also explain how these advantages will assist you when working with databases. And you're also able to provide a high-level overview of how SQL, DDL, DML, and DQL syntax is used, and identify the main SQL commands used in databases. In the final lesson of this module, you explored basic database structure. Now that you've reached the end of this lesson, you can explain the concept of a database table and outline what it's used for, and identify the key components of a database table, such as columns, rows, data types, and keys. You are now familiar with the basics of databases. You can explain how they store data, identify methods for interacting with databases through SQL, and outline the basic structure of a database. That's a great start to your database journey. Well done. You probably know that database tables store data in the forms of columns and rows. But how do you make sure that every column accepts the correct type of data? For instance, that your cost column stores values in decimal, or your product quantity column accepts positive numbers. This is exactly what data types do. With data types, you can determine what kind of data is accepted by each field in your table. Over the next few minutes, you'll learn how to explain a numeric data type in a database and differentiate between integer and decimal data types. Before you begin exploring numeric data types, let's take a moment to explore the concept of data types. When you create a table in a database, you need to define column names and the data type of the content that will reside in those columns. Data type tells a database management system, such as MySQL, how to interpret the value of the column. Data types maintain data in the right format and make sure the value of each column is as expected. The most used data types are numeric, string, and date and time data types. Let's take the example of a table from the database of an online store. This table collects information on customers in the form of columns called customer name, order date, product quantity, and total price. Each of these columns must store data in the form of a suitable data type. The customer name column can use string data, order date can use a date type, and product quantity and total price columns are best suited to numeric data. The focus of this video is the numeric data type. Numeric data types is the generic term used for all specific data types that let a column store data as numbers in the database. The two most common numeric data types used in databases are the integer data type, used for a whole number value, and the decimal data type, used for a number with a fraction value. To return to our earlier table example, the product quantity column is defined as an integer data type. This is because it holds whole numbers only. Fractional numbers can be inserted, but they'll always be automatically rounded up or down to the nearest whole number in the database. And the total price column is a decimal type. This is because it holds fractional numbers. For example, an item that costs $80.90 is a fractional value. 80 is a whole number and 90 is a decimal. Whole numbers can also be inserted. The database will add a decimal point along with a fractional value of 0. In most database management systems, you'll find different types of integer and decimal data types. Each type is intended to store a minimum and a maximum number value. For example, in MySQL database management system, tinyInteger, or tinyint, is used for a very small integer number value where the maximal possible value that can be inserted is 255. While integer or int can be used to store a very big number, the maximum value that it can store is over 4 billion. These data types can also accept negative and positive values. In some database management systems, you can also force columns to accept positive numbers. This increases the maximum value they can store. You should now be able to explain the numeric data type in a database, and you should also be capable of differentiating between integer and decimal data types. Great work. You probably already know that when you create a table in a database, you must define the column names and the data type of the content that will reside in those columns. You can use a string data type to define a column's data type, particularly in instances when it accepts both numeric and text characters. In this video, you'll explore the string data type, and by the end of the video, you'll be able to explain the string data type in a database and differentiate between char and varchar data types. When you create a table in a database, it is important for data integrity to ensure that only valid values are inserted in your table. For example, you should use string data type when you intend to store data that contains a mix of character types. So if you define a column as a string, then any type of text can be inserted. This includes alphabet characters, numeric characters, and special characters. Let's explore an example to find out more about how string data types work. Let's take the example of a student table from a college database. This table stores student login information for the college's online portal. It stores this information under the following 4 columns: student name, username, password, and email address. The student name column contains only alphabet characters. The username column contains alphanumeric characters, and the password and email column contains a mix of character types. String data type is a generic term used for different string data types in the database. The most used string data types are char, which stands for character. This data type is used to hold characters of a fixed length, and varchar stands for variable character. This holds characters of a variable length. Let's explore these string data types further. Char means that the given length of the characters is predetermined. It can't be changed after declaration. Column attributes are defined as char followed by a character length in parentheses. For example, char 50 means that a column only permits 50 characters of space in each field. Char is the best option if you have a predefined size of character that you want to maintain. In the student table, you can set a maximum length of 50 characters for the username column in SQL with char 50. For example, the table contains the records for a student with the username Mark123, which is a total of 7 characters. However, because the column is defined as char 50, this username occupies a length of 50 characters within a space. The varchar data type works in a similar way to char. However, it is a variable length. This means that the length can be changed, it's not fixed. Varchar is often used when you're not sure how many characters might be inserted in a column field. So you can type varchar 50 in SQL to allow for any input up to a maximum of 50 characters. In the student table example, the student name column would most likely contain names of varying length. So you could define the student name column as varchar 50 in SQL. This means that the name of each student only occupies as much space as there are characters in their name. For example, Mark Simpson occupies far less than 50 characters, but this field could hold a name up to the value of 50 characters if required. Finally, let's briefly explore some more commonly used examples of string data types. Tiny text is used to define columns that require less than 255 characters, like short paragraphs. Text is used to define columns of less than 65,000 characters, like an article. Medium text defines columns of 16.7 million characters, for example, the text of a book. And the long text data type stores up to 4 gigabytes of text data. You should now be able to explain the string data type as used in a database, and you should also be capable of differentiating between string data types, including char and varchar. Great work. To ensure the accuracy and reliability of the data in your database, you must limit the type of data that can go into your database table. In this video, you'll learn how to describe the purpose of constraints in a database and identify default constraints to set default values in a table. Database constraints are used to limit the type of data that can be stored in a table. This ensures that all data inserted into the table is accurate and reliable. If the database detects a violation between the constraint and the data operations, then it aborts these operations. An example of a violation might be an attempt to insert or upload invalid data to a table. The database realizes that the data is invalid and rejects it. Constraints can be column level, where the rule applies to a specific column. They can also be applied at table level. For example, I could use the foreign key constraint to prevent actions that would destroy links between tables. I'll demonstrate this in more detail in a later lesson. Two of the most used database constraints include not null, a method of preventing empty value fields, and default, a method of assigning default values. For now, let's begin our exploration of default values with the not null constraint. The not null SQL constraint is used to ensure that data fields are always completed and never left blank. Let's explore this concept using the example of a table from an online store that records the IDs and names of customers. The table records this data in its customer ID and customer name columns. These columns must always contain data. If there's no data or values inserted into either of these columns, then the creation of a new customer record is aborted. The not null default value is implemented using a SQL statement. A typical not null SQL statement begins with the creation of a basic table in the database. I can write a create table clause followed by customer to define the table name, followed by a pair of parentheses. Within the parentheses, I add two columns, customer ID and customer name. I also define each column with relevant data types, int for customer ID as it stores numeric values, and varchar for customer name as it stores string values. Finally, I also declare a not null constraint for each column. This makes sure that neither column will accept null values. Now, any operation that attempts to place a null value in these columns will fail, like inserting or updating data. Next, let's look at how the default constraint works in a table. The default constraint sets a default value for a column if no value is specified. This means that if no data is entered for a specific field within a column, then a table will automatically insert a default value instead. To gain a better understanding of default values, let's look at a table that holds player records for a football club's database. The table is called Player Table and contains two columns. The first is player name and lists the names of each player in the team, and the second column is city and lists which city each player is from. Most of the players in this club are from Barcelona, so I can specify a default value of the city column as Barcelona. This means that I don't have to enter Barcelona repeatedly into the city field for each new player. If no value is entered in the table, then each field is automatically filled with the default value of Barcelona. Let's find out how the default command is incorporated into a SQL statement. First, I use the create table commands to create a table, and then call it player. Then within a pair of parentheses, I input the column names, assign a string data type for each, and assign a default value of not null for the name column. Finally, I add the default keyword statement, followed by the default value Barcelona for the city column. Now when I add data into the table for a new player, I don't need to type in Barcelona for players who are from the city. Instead, it will be inserted automatically. You should now be familiar with the importance of using database constraints. You should also be able to explain database constraints as a method of enforcing rules on a column or table level. Good work. You've just been hired by an online bookstore to build and maintain databases that can store information on millions of books and customers. But how do we even begin to create and alter databases that store constantly expanding information or process millions of orders from all over the world? The answer to these questions lies in SQL create and read commands. In this video, you'll learn how to create a database using SQL syntax, and you'll also discover how to drop or delete a database. However, before you create a database, you first need a clear idea of its purpose. For example, if you're building a database for an online bookshop, then your database needs to record data like book titles, authors, customers, and sales. The data on these topics must be stored and organized in relevant tables in a database. Users can then access, retrieve, and update the data as needed. So how can you create a database using SQL syntax? To create a database, just type the create and database keywords. These keywords are then followed by the name of your database. But what about removing or dropping a database? To drop a database, just type the keywords drop and database. Then follow these keywords with the name of the database you want to remove. Let's look at these keywords in action. To create a database, I need to use SQL syntax. To demonstrate, let's create a second bookstore database using SQL syntax. First, I type the keywords create and database, followed by the name of my new database. In this case, the database is called bookstore2_DB. I always use a meaningful and relevant name when creating a new database. This helps to make it easier to document my work. Database names must also be unique and can only have a maximum of 63 characters. If my database name doesn't meet these requirements, then an error message will appear. Finally, I add a semicolon to the end of the statement. Then I run the statement, and the new database bookstore_db2 appears on the left-hand sidebar. So, I've created a second database. I can also remove databases using SQL statements. First, I select the SQL tab. Then I input my query in the code box that appears. I type the keywords drop and database followed by the name of the database I want to delete. In this case, it's bookstore_db. Now I run the query. Then SQL deletes the database. In this video, you learned how to create and delete databases using SQL syntax. Great work. Building a database involves working with substantial amounts of data. But how do you organize your data so that you can find exactly what you need and make sense of it? With SQL, you can create a table within your database to hold and organize your data. In this video, you'll learn how to create tables in a database management system using SQL syntax. Let's begin with a look at the SQL create table statement syntax. I begin the statement with the keywords create table to let SQL know that I want to create a new table. I then add the name of the table I want to create. Finally, I add a pair of parentheses. Within these parentheses, I type the name of each column that must be included within the table, followed by its respective data type. Now that you're familiar with the syntax, let's look at it in action. Be aware that before you can create tables, you must already have a database on the server. In other words, you can't build tables if there's no database to create them in. So let's assume that I already have a database ready to work with. In this example, I'll create a customer table in the bookstore database to store customer data, like names and phone numbers. First, I write a SQL statement that contains the create table commands followed by the name of the table, in this case customers. Then I add an open parenthesis. It's within this parenthesis that I need to create my own columns. So, I write the name of my first column, which is customer name. This is followed by the data type varchar. This data type means that the column can hold data of any type. I then add a numeric value within a pair of parentheses. Then I add a comma and write the name of the second column, which is phone number. I add int as the data type so that only whole numbers can be stored. Then I add a closing parenthesis and a semicolon. Finally, I execute the statement. The customers table is now stored in the database. In this video, you learned how to create tables in a database using SQL syntax. Well done. At this stage, you're probably familiar with creating tables in databases, but no table is ever static. Database developers are always restructuring tables. Sometimes they need to add new columns, delete old ones, or edit the data they contain. You can complete many of these basic restructuring actions using SQL syntax. In this video, you'll learn how to alter a database table by adding and removing columns, and modify the attributes of a database table. Let's start by exploring the SQL alter statement syntax. The first part of an alter statement is the alter and table keywords. These keywords inform the database that there is a table whose contents must be altered. This is followed by the name of the table to be altered. I then include the add keyword. This keyword tells SQL that there's one or more items to be added to the table. There are other keywords I could include here instead, but for the purposes of this example, I'll work with add. Finally, I insert a pair of parentheses. Within these parentheses, I declare the name of a new column to be added to the table, along with this data type. Now that you're familiar with the alter table statement, let's explore an example of this statement in action. However, before you can begin altering tables, you must already have a database on the server. So, as always, make sure that you know how to create databases before proceeding, and ensure that you already have a table in your database with data that you can alter. In my example, I have a students table located within the database called college. My students table holds information on the IDs, names, and emails of each student in a college. I can demonstrate the alter statement by adding, deleting, and modifying columns in this table. My first task is to add 3 new columns to the table: age, nationality, and country. To add these columns using SQL syntax, I first type the alter table command, followed by the name of the table, students. Next, I use the add command to let the database know that I want to add new columns to the table. Then I input a pair of parentheses that contain the columns I want to add, along with the type of data they'll hold. These columns are an age column, which holds data in integer format, a country column with varchar as the data type, and nationality and country columns that hold varchar or string data. I also add a character limit of 50 to the country columns fields and a limit of 255 to the nationality columns fields. Then I execute this statement. I now have 2 new columns in students table in the college database. Country and nationality are very similar columns, and in most cases will probably hold the same type of information. So I can write a SQL statement to remove the nationality column. Just like the last example, I start my statement with alter table students table. Next, I type the drop column command followed by nationality. This command instructs SQL to delete or drop this column from the table. Then I run the statement. A notification message appears requesting confirmation of deletion. I press OK to confirm. The nationality column has now been dropped. Now it's time to alter the structure of the table. The country column has a limit of 50 characters, just as I said it originally. But now I'm going to change it so that it holds 100 characters instead, using the alter table command. I start with the syntax alter table, followed by students table. Then I type the modify command, the country column name, and the varchar data type. And finally, I add a pair of parentheses containing my new value of 100. I then execute the query. My country columns limit has now been updated to 100 characters. In this video, you learned how to alter and modify tables in a database using SQL syntax. Well done. When working with databases, you'll often have to add new rows and columns to existing tables or even create new tables from scratch. For example, if you run a college database, you'll have to add new rows for every new student. With SQL, you can perform these tasks quickly using the insert statement. By the end of this video, you'll be able to identify and understand insert SQL syntax and insert data into tables with the use of the insert into clause. Let's begin with an exploration of the insert into syntax. To write an insert statement, first write an insert into clause. Then specify the table name followed by a list of columns contained within a pair of parentheses and separated by commas. Then use the values keyword and write a list of values within a pair of parentheses. It's important to remember that each value corresponds to a specific column and so should reflect the same data type and order. You can also add multiple rows into a table at the same time. First, write the insert into clause in table, just like before. Then use the values keyword and add multiple rows of values. Just make sure that each new row is separated from a previous one by a comma. Now let's explore some examples of an insert statement. In this example, I'll use a table called players from a sports club database, and I want to insert new player data into this table. First, I write the insert into command, followed by the name of the table. In this case, it's players. Then I add the column names within a pair of parentheses. These columns must contain the basic information that the club requires about each player. So I'll name the columns ID, name, age, and start date. Next, I insert the values keyword and then add the values I want to assign to each column within a pair of parentheses. I start adding the data for a new player named Yuval, age 25, with an ID of 1 and a start date of 2020-10-15. 15. It's important to use the correct format of year, month, and day when entering dates in a table. Otherwise, an error message will appear. I can also use the current date function followed by a pair of empty parentheses next to my values, just like I've done for the new player Yuval. Now that I've scripted all values for Yuval, note that each value relates to a specific column. Number 1 corresponds to the player ID column, Yuval to player name, 25 to player age, and the date to start date. This means that the order in which I type my values within the parentheses is very important. Otherwise, I might accidentally store these values in the wrong columns. It's also important to note that all non-numeric values are placed within quotation marks, just like Yuval and the date value in the statement. Finally, I execute the statement. The output now shows one row of data for Yuval, just as my code instructed. But what if I wanted to insert multiple records of data into the table? Let's say that 2 new players have joined the team. The first player is Mark, age 27, with an ID of 2 and a start date of 2020-10-12. And the second player is Carl, age 26, with an ID of 3 and a start date of 2020-10-7. Both Mark and Carl must be inserted into the database. As you learned earlier, this is a very straightforward task. First, I write the insert into command. Then I write the table name, players. Next, I type the ID, name, age, and start date columns within a pair of parentheses. Then I write the values keyword and insert 2 records of data. These data records are contained within 2 pairs of parentheses separated by a comma, one for Mark and another for Carl. Finally, I run or execute the statement. I then check my output, which shows that all 3 players are now in the table. So far, I've explored how to add data to the table, but it's also possible to show existing data in the player table by executing the following SQL query. First, I type the select clause, followed by an asterisk. This asterisk tells SQL to return all columns within the table. Then I type the from keyword and the name of the table. I execute the statement, and the output shows all data available from the player table. You can now identify and make sense of the insert syntax, as well as insert new data into tables with the insert into clause. Good work. There will often be times that you'll need to query data from a table in your database. For example, you might need to retrieve a list of names from a table, or return a set of results from a math calculation. You can perform these actions using the select statement. And that's what I'll demonstrate now. So over the next few minutes, you'll learn how to utilize the SQL select statement to query data from a table in a database, and perform other SQL select tasks, such as math calculations, date and time queries, and concatenation functions. To get started, let's explore the syntax of a SQL statement. A basic SQL select statement is written as the select keyword, the name of the column that contains the data you need to query, then the from keyword, and finally the name of the table you want to query. For example, if I want to query data about the names of players from a soccer club database, I could use the following syntax: the select keyword, the player name column, and the from keyword, and finally the name of the table, which is player table. And although it's not mandatory, a semicolon is often added to mark the end of a SQL statement. Let's take a closer look at how this statement works. As an example, I'll extract information from a table called players held in a soccer club database. This table records details about players in a soccer club like ID, name, age, and skill level. I can use the SQL select statement on this table to obtain information on the club's players. The expected outcome of this select query is that it will return a result set that displays all player names held in the table. I can write the statement as select name from players. The select command is used to retrieve data. Name is the column that stores the player's name in the database. From is a keyword that identifies the source table, and players is the table name. I then run the statement. The query returns a table column that lists the players' names from the players' table, with each name on its own row. So in the example you just explored, I retrieved data from one column in a table. But what if I wanted to retrieve data from multiple columns? Maybe I need to retrieve the name and skill level of each player. I can obtain this information using a SQL select statement written as select name level from players. I add a comma between name and level so that SQL understands they are two separate columns. I run the query and it returns the data from the name and level columns in the players table. I could also use the select statement to retrieve all data from all columns in the players table. There are two methods I could use to achieve this. The first method is to list all column names in a standard select statement as follows. Select ID, name, age, level, from, players. Once again, each column is separated by a comma. I then run the query and get all the requested information in table format. The second method is to use an asterisk as shorthand. So instead of typing out all column names, I just type select, asterisk, from, players. Then I run the query. It returns all the information available in all table columns, just like in the first method. You're now familiar with how to use the select statement in MySQL. So, next time you need to query data in your database, you've now got different methods to choose from. When working with tables, there might be instances where you need to retrieve information from one or more tables in order to populate columns in another table. You can complete these actions using the insert into select statement. Over the next few minutes, you'll explore the SQL syntax for these actions, and by the end of this video, you'll know how to identify and understand insert into syntax and insert data from a source table into a target table using the insert into clause. First, let's find out more about the insert into select statement. Essentially, the insert into select statement is used to query data from a column within a source table and place the results of that query in the column within a target table. For example, you could use an insert into select statement to query data in column C in the source table and place the results of that query in column B of the target table. So what does the insert into select statement syntax look like? Here's an example. First type an insert into clause, followed by the name of the target table and the name of the column you want to insert data into. Then type the select keyword with the name of the column you want to extract data from, and finally, type a from keyword and the name of the source table that holds that column or source data. To find out more about how this syntax works, let's explore an example of insert into select. To demonstrate the statement, I'll use tables from a soccer club database that contain important data about the club. However, before I begin querying this data, let's quickly review these tables. In this database, I have a table called players that holds the records of 4 different players in the team. I also have a table called country that holds information about the countries that these players are from. But right now, the country table is missing the names of the countries. In other words, it has no data. I can perform a SQL query using the insert into select statement to populate this missing data. Do you remember the example of the source and target tables from earlier in this video? In this instance, the player table is the source table that I need to query, and the country table is the target table in which SQL places the results from my query. So, to query data from my source table and populate my target table with it, I write an insert into select statement. Note that for the purposes of this demonstration, I have organized the player data in the player table in the same order in which it must appear within the country table. So to perform this task, I first click on the SQL tab to open the code editor. Then I write an insert into command, followed by the name of my target table, which is country table. I then state the name of the column that the data from my query must be inserted into within a pair of parentheses. In this instance, the column is called country name. Next, I type the select keyword and state what column I want to query within the source table, which is country. Finally, I type the from keyword and state the name of the source table I want to query the data from, which is player table. I add a semicolon to the end of my query, then run it. Now I select country table, my target table from the database, and check that the country name column has been populated with the correct data. You now know how to query tables using the insert select statement. Well done.
I recently created a database table for a college called Student Table. It contains the following pieces of data on each student in the college: ID, first name, last name, home address, college address, contact number, and department. Let's use the update syntax to update the home address and contact number of the student assigned the ID of 3 in the table. So I click the SQL tab in PHP MyAdmin. Now I use the update clause followed by the name of the table that I want to update, which is student table. Then I add the set clause, followed by the names of the columns to be updated, which are home address and contact number. Next to the name of each column, I add an equal to symbol and place the new values to be inserted into the table in single quotation marks. I also make sure to separate these column value pairings with a comma. Finally, I add the where clause to identify the exact record I want to update. This record has a student ID column field that was assigned the value of 3. So I write where ID equals 3. Now that I've completed the syntax, I can select Go. I then receive a message confirming that the change has been made, and when I check the table, it displays the updated values for the assigned columns alongside student 3. So that's how you update the information for one student. However, the update syntax can also be used to update the information for multiple students at once. Let's suppose that the college's engineering department has moved their classes to a new location on campus called the Harper Building, and I need to update the department's address on the table for all engineering students. I can perform this task using the update SQL syntax. The syntax is very similar to the previous example. First, I use the update clause followed by the name of the table. Then I add the set clause and state that I want to update the values within the college address column to Harper Building. So I type this as set college address equals Harper Building. Next, I type the where clause and state that I want this update to occur within the college address column for all students assigned the value of engineering in the department column. I then click Go to run the statement. Now, I just check that the table has updated the college address of the engineering department to Harper Building. I could also use the update statement to update multiple field values in multiple records. For example, I can return to the original SQL statement and add a new column value pairing to the set clause. If I want to update the home address column, I add a comma and write home address equals the new address information within quotes. Make sure to separate out the column value pairings with a comma. In this example, I'm updating 2 columns with one update statement. In this example, I'll demonstrate how to delete a single record from a table in a database. I'm using the student table from a college database and deleting the record of a student with the last name of Miller. I go to the SQL tab in PHPMyAdmin, and I write a delete statement beginning with the keywords delete from. Then I specify the table name as student table. I add a where clause and the condition to delete the data I want. I need the database to scan the list of students and identify the last name or value of Miller, and then delete that record from the table. So I type where, followed by last name, equal to Miller. I then run this statement by pressing the Go button. I get a confirmation that the record Miller has been deleted from the database. I can then access the student table on the left panel to ensure that the record or instance of Miller has been removed. Let's explore another example, this time by deleting multiple records from the student table. Now I want to delete the records for the 2 students within the engineering department. The beginning of the statement is the same as the previous example. I begin with the delete and from keywords, followed by the name of the table I'm working with, which is student table. The where clause is the key difference in this example. I type where, followed by department equal to engineering. This instructs SQL to identify all records that have a value of engineering within the department column and remove those rows from the table. But I need to be careful. If I don't correctly specify the where clause, then all the records in the table will be deleted. So now that I've completed my statement, I select Go to run it. I then check the table by clicking it on the left panel and confirm that the records for the 2 engineering students have been deleted from the table. Finally, let's quickly explore how to delete all records from a table. In this task, the syntax remains largely the same as in the previous examples. The key difference is that I remove the where clause so that now my syntax just states delete from student table. I remove the where clause so that now my syntax just states delete from student table. In other words, I'm instructing the database to remove all records from the student table. Then I click Go and confirm the deletion. Once the deletion has been confirmed, I check the student table, which is now empty. I now know that all records have been deleted.
You've reached the end of this module on CRUD operations. In this module, you've discovered how to create, read, update, and delete data within a database. You've also examined different SQL data types like numeric, string, and default values. It's now time to recap the key topics you learned and skills that you gained. You began the module with an introduction to SQL data types. Following the completion of this first lesson, you can now identify and understand the numeric data type so that you can store data as numbers in a database, utilize numerical data types in a database, and differentiate between integer and decimal data types so that you can store numerical values of different sizes, including positive and negative ones. Following your exploration of numerical data types, you then moved on to investigate string data types. During your investigation, you learned how to identify and understand string data types in a database, demonstrate how to use string data types, and outline the key differences between char and varchar data types. The final concept that you learned about in this lesson was default values. Now that you've completed the lesson on default values, you're able to demonstrate an understanding of the concept of constraints in a database with SQL syntax and identify the default constraint to set default values in a table. As part of this lesson, you also undertook a series of exercises focused on SQL data types. Having successfully completed these exercises, you can now demonstrate your ability to work with numeric data types, string data types, and default values, and outline how to select the correct data type for your data. Once you completed your study of SQL data types, you then moved on to explore the topic of creating and reading data in a database. Now that you've completed this lesson, you're able to create a database and create tables, alter database tables, and drop a database. You can also demonstrate how to create a table in a database with SQL syntax, alter table structure using the SQL alter table statement, and insert or add data into a table with SQL insert statement. In addition to these new skills, you also learned how to retrieve data from tables with the SQL select statement and insert query data from one or more tables into another target table using the insert into select statement. You also had an opportunity to demonstrate these new skills through a series of exercises. In these exercises, you proved your ability to create a database and a table, and then populate the table with data, and manage data within your tables using the select and insert into select statements. You then moved on to the final lesson, in which you explored how to update and delete data. Having completed this lesson, you can now demonstrate knowledge of the SQL update statement, and utilize the update statement to update both single and multiple field values of a record. Finally, you also proved your abilities with these new skills by completing an exercise in which you deleted records from a table. You're now familiar with the create, read, update, and delete operations. You're also skilled in the use of SQL data types. Great work. You're making good progress on your learning journey. Imagine a corporate database with information about hundreds of employees. How can you calculate important things such as salary increases or calculate changes to allowances for all the employees accurately and efficiently? With SQL, you can use arithmetic operators to make these adjustments. By the end of this video, you'll understand and be able to describe SQL arithmetic operators and know how to use these arithmetic operators to perform functions in SQL. But first, what exactly are operators in SQL? Operators are specific words or characters that help you to perform different activities in a database. They're like conjunctions or connection words you would use to compose a sentence, or the operation keys used to perform a sum in a calculator. So, why do you need to know about operators? Well, when handling data in a database, at some point you'll need to query and manipulate data for different purposes. SQL operators allow you to manipulate data as necessary to perform these different activities in the database. For example, you can use an arithmetic operation to calculate how many leave days an employee has left, or you can compare whether employees are meeting company targets. There are various types of operators in SQL, each with different functions. Let's explore a few examples of arithmetic operators. Arithmetic operators are commonly used in computer languages to perform a calculation and return a result. Much like common arithmetic operators in mathematics, you can use arithmetic operators in SQL to carry out mathematical operations in a database. The SQL arithmetic operators and their symbols are plus for addition, minus for subtraction, and asterisk for multiplication, / for division, and percentage for modulus, which provides the remainder value of a division calculation. So how do SQL arithmetic operations work? When performing a calculation, an operator takes two operands and returns a result. For example, an addition operator can take 5 as both of its operands and return 10 as its result. In SQL, you can apply the same concept by using the select command for the various operations. Let's illustrate this concept using the addition operator. You can use the select command, followed by one operand, the addition operator, and the second operand, and just like the previous example, SQL calculates the two operands and produces the result. You can repeat the SQL syntax with the other arithmetic operators. With a subtraction operator, the output result is 0. A multiplication operator returns a result of 25. The division operator calculates the result as 1. And with a modulus operator, the result is 0, as 5 divided by 5 equals 1 with no remainder. Now, let's take a closer look at how to use these arithmetic operators in SQL. I'll demonstrate how to use arithmetic operators in SQL to perform basic mathematical operations. Let's try an addition operation to add two numbers. First, I use the select command and then type the numbers 10 and 15 separated by a plus operator, followed by a semicolon. Although the semicolon is optional in this case, I prefer to still use it as it represents the end of a SQL statement. The select command retrieves the value, which is the sum of 10 plus 15, and displays it on screen. Let's run this query. The query produces the result of the example addition operation, which is 25. Just as I performed this addition operation, I can do the same with subtraction, multiplication, division, and modulus operators. I can use the minus sign for subtraction, an asterisk star for multiplication, / for division, and a percentage sign for modulus. For example, I can type select 100 modulus 10. This divides 100 by 10 and gives me the remainder of the division operation. In this case, the remainder is 0, as 100 divided by 10 equals 10 with no remainder. So, I run the query and the remainder of 0 is displayed. And that's how you can use the operator symbols for different basic operations in SQL. You've learned about SQL arithmetic operators and how to perform basic operations with them in SQL. You're now ready to learn how to apply these arithmetic operators in more practical ways. Awesome work.
So far, you have learned how to use SQL arithmetic operators to perform basic functions. In this video, you'll take one step further by learning how to use these arithmetic operators in practice when working with a database. Let's explore the use of arithmetic operators using the example of a corporate table of employee data. It's populated with the following information about each employee: ID, name, and salary. I'm going to demonstrate how to use each of the arithmetic operators in SQL to perform various functions with this practical data and retrieve the desired results. In this first example, let's say that an employer wants to give each employee on their team a $500 bonus. But first, they'd like to see what each employee's salary looks like after adding the $500. I can type select salary plus 500 from employee to add the $500 bonus to each employee's salary. This select command works by retrieving the salary of each employee from the employee table and then adding $500 to each value. Let's execute the query by clicking the Go button. The result is that each employee's salary has increased by 500. You can create other statements that use the select command in a similar way. For example, let's say the employer wants to deduct $500 from the salary of each employee. To do this, I type the SQL query statement, select salary minus 500 from employee. Again, I'm using the select command to retrieve the salary value of each employee record stored in the employee table. This time, I use the subtraction sign, minus, to subtract $500 from the salary of each employee. Now I click the Go button, and the database returns a table that shows the output result of salaries after the deductions. In the next example, let's imagine a scenario where the employer would like to increase the employees' salaries by doubling their current annual salary. To do this, I use the select command to perform the same function as discussed previously. I then use the multiplication sign, an asterisk symbol, to multiply the salary value of each employee by 2. So the SQL statement now reads, select salary asterisk 2 from employee. I can now click the Go button to generate an output of the results of salaries from multiplying the values by 2. Now let's suppose the employer needs to determine the monthly salary of each employee. I can perform this task using an SQL query statement as I have done in the previous scenarios. However, this time I'll divide the annual salary by 12 months. To determine the monthly salary, my statement reads as follows. Select salary / 12 from employee. The select command retrieves the salary value for each employee stored in the employee table. Then division sign, or the / divides the annual salary value by 12. So I click the Go button to generate the output result. The employer can now use this output result to determine what each employee's monthly salary is. In our final example, the employer would like to know if the ID of each employee is an even or odd number. I can use the modulus operator to complete this task. I just need to type the following statement. Select ID modulus 2 from employee. I then click Go to execute the statement. This divides each employee ID by 2 and returns the remainder of the division operation. In this case, a remainder of 0 denotes an even ID, as all even numbers are divisible by 2, meaning there will be no remainder. The result shows that there are 3 odd IDs and 2 even IDs. You should now know how to make use of the SQL arithmetic operators in a database. You're making great progress. Keep it up.
Imagine you're running a database for a soccer club. As a database engineer, there's a lot of work required to manage this database. For example, you might need to categorize players into groups according to their ages. How can you complete this kind of task? You can use SQL comparison operators. Over the next few minutes, you'll learn how to explain the concept of SQL comparison operators and utilize SQL comparison operators in a database. So, what are SQL comparison operators? Comparison operators are used to compare two values or expressions where the outcome result can be either true or false. They can be used to filter data and to include and exclude data. So how are these operators used in SQL? SQL uses common mathematical comparison operators by means of the symbols equal to, less than, and greater than. It also uses less than or equal to greater than or equal to, and not equal to. Now, let's explore how to use these comparison operators and relevant symbols in a practical way using a database. To demonstrate the use of SQL comparison operators, I'll use the example of an employee table from a company database. This table includes information on each employee's ID, name, and salary. Now, let's assume the employer wants to extract relevant data from the employee table about the employee's salaries for different purposes. Each instance of data extraction will require a different comparison operator. So, in the first example, the employer wants to identify all employees receiving a salary equal to $18,000 per year. I can identify these employees using the equal to operator. First, I click the SQL tab in the main menu. Then I write select, asterisk, from, employee, where, salary equal to symbol, 18,000. Let's break this SQL statement down. The select command is used to retrieve data. The asterisk star denotes that I am selecting data from all columns. The from keyword and the table name specify where the data will come from, and then I define the condition using the where clause. In this case, the condition uses the equal to symbol to check if the salary value in each record of the table is equal to $18,000. If the result is true, then the data is retrieved. So, I run the query and generate an output. The output result of this query is that the employees Carl and John earn $18,000 per year. You can apply the other comparison operators in a similar way to perform different functions. Let's take another example to find out more. In this next example, the employer needs to know which employees are receiving a salary that is less than $24,000 per year. This task requires a different operator. To find this information, I can write select, asterisk, from, employee, where, salary, less than symbol, 24,000. This SQL statement utilizes the less than symbol to check whether the value stored in each field of the salary column is less than $24,000. Once again, I select the Go button to execute the query and generate an output. The output of this query is that the employees Carl and John earn less than $24,000. Let's take another example where the employer needs to determine which employees receive a salary that is less than or equal to $24,000 per year. In this case, I need to write the following query: select, asterisk, from, employee, where, salary, less than or equal to symbol, 24,000. The only thing in this statement that has changed from the previous example is the operator symbol. This less than or equal to symbol tells the SQL statement to check whether the value stored in each field of the salary column is less than or equal to $24,000. I click the Go button to execute the query. The output results show that there are 4 employees who earn less than or equal to $24,000 per year. What if the employer wants to know which employees receive a salary that is greater than or equal to $24,000 per year? To generate these results, I can use the greater than or equal to operator in my SQL statement. So I write the following SQL query: select, asterisk, from, employee, where, salary, greater than or equal to symbol, 24,000. This time, the greater than or equal to symbol is used to check whether the value stored in each field of the salary column is greater than or equal to $24,000. I click Go to execute the query, and the output shows that there are 3 employees who earn $24,000 or more per year. The final comparison operator available in SQL is the not equal to operator. In this final example, the employer wants to know which employees receive a salary that is not equal to $24,000 per year. I can determine this using the following SQL code: select, asterisk, from, employee, where, salary. Then I type less than and the greater than symbols to denote the not equal to operation, and then I type 24,000. As with the previous operators, the SQL statement utilizes the operator to check the values stored in each field of the salary column. In this case, it checks for values that do not equate to $24,000. The output results of this query show that there are 3 employees whose salaries are not equal to $24,000 per year. You should now be able to describe comparison operators and use them in a database in SQL. Congratulations on building another important database skill. There are several clauses available in SQL for sorting and filtering data in a table. One of the most useful of these is the order by clause. With this clause, you can reorder the data in a table by one or more columns. For example, in a table that holds data on students in a college, you could sort the data by date of birth. The table would then present all students in the order of oldest to youngest. By the end of this video, you'll be able to demonstrate the purpose of the order by clause for sorting data, explain the different forms in which the order by clause can be used to sort data, and describe how the ascending and descending keywords behave when used on sort columns. Let's begin with an exploration of the purpose of the order clause. The order by clause is an optional clause that can be added to a select statement. Its purpose is to help sort data in either ascending or descending order. For example, you can sort a list of student names in an alphabetical order from A to Z or vice versa. To get a better understanding of how the order by clause works, let's explore the syntax. In its most basic form, the syntax of the order by clause is as follows. It begins with a select statement, then a list of the columns to be sorted with each one separated by a comma. Next is a from keyword, followed by the name of the table to be sorted. Finally, the order by clause is added, followed by the name of the column to be sorted. At the end of the column name, state how you want the data to be sorted. You can do this by specifying ASC for ascending order or DESC for descending. But the order by clause doesn't limit you to just the one column. You can also use this syntax to order the data from multiple columns. The syntax for sorting multiple columns is very similar to that used for a single column. The key difference from multiple columns is that you must type the name of each column after the order by clause. Just make sure that you separate each column with a comma, and specify whether you want to sort the columns in ascending or descending order. It's also possible to specify all columns after the select keyword by using an asterisk. This is a much easier method than listing all columns one by one. Finally, it's also important to note that the type of data in your table affects how it is sorted. If the column has a numeric data type, the records will be sorted in the ascending or descending numerical order. And if a column has a text-based or string data type, then it will be sorted in ascending or descending alphabetical order. Next, let's explore some examples of the order by clause in a SQL statement. Let's begin with an example of ordering data by a single column. For this example, I'll use a table that lists details of students in a college. I need to sort or order this data in ascending order of each student's country of nationality. So in this instance, the order by column must be the nationality of each student. Each student's nationality is listed in the table's fifth column. I begin by writing the select statement, followed by the names of the columns that I want in the result: ID, first name, last name, and nationality. Then I write the from keyword, followed by the name of the table, which is student table. Next, I type the order by clause. Then I specify the name of the column by which I want my data to be sorted, which is nationality. Finally, I type ASC so that the data is sorted in ascending order. I then execute the statement. All students in a table have now been sorted according to nationality in ascending order. Note that even if I was to omit ASC from the end of my code, I'd still get the same result. This is because the order by clause sorts all data in ascending order by default. Let's run the same statement, but this time using DESC or descending instead of ASC. All students in the table have now been sorted by nationality for a second time, but in this instance, they've been sorted by descending or reverse alphabetical order. Finally, let's explore an example of sorting data by multiple columns. In this example, I'll sort each student by nationality and date of birth. First, I write the select statement. Then I write the names of the columns I want in my result: ID, first name, last name, date of birth, and nationality. I then write the from keyword and student table, the name of the table. Next, I type the order by clause and specify the names of the columns by which I want my data to be sorted, which are nationality and date of birth. I then add ASC after nationality, so that the data is sorted in ascending order of nationality. And I add DESC after date of birth, so that the data from this column will be sorted in descending order. Then I run the statement. This returns my table with the data for the specified columns organized as instructed, which is alphabetically for nationality and youngest to oldest. This was a short introduction to the SQL order by clause. You can now demonstrate the purpose of the order by clause for sorting data, and you can also explain the different forms in which the order by clause can be used to sort data. Great work. An admin department at a university wants to create different reports for students in the engineering faculty. The department needs to filter out students from the engineering faculty to retrieve their details from the student database. So how can this be done with SQL? Well, the where clause is useful in scenarios like this. In this video, you'll learn how to explain the purpose of the where clause, demonstrate how to filter data using the where clause, and make use of different operators in the where clause condition. So what is the where clause? The where clause is used to filter data. More specifically, it is used to filter and extract records that satisfy a specified condition. To better understand how the where clause is used, it may help to break down its syntax in a SQL select statement. The syntax begins with a standard SQL select statement, followed by the columns you want to query. Next is the from clause, followed by the table name. Then you can bring in the where clause. After the where clause, you can specify a condition. You may be wondering what the purpose of the condition is. Well, the condition makes it possible to filter out and fetch the required records from the table. You can think of the conditions as filter criteria. Only the records that meet the condition will be retrieved. For example, you can use the condition or filter criteria to check if the desired column name is equal to a certain value or operand. In between the column and value, you can place an operator. As you've just discovered, the operand follows the operator. Let's take a quick look at it in more detail. The operand can be either a text value or a numeric value. It all depends on the data type of the table column or field. To demonstrate, let's take an example where student ID equals 01. In this case, the condition is instructed to filter a numeric value, so it functions as a filter criteria. Once you run the SQL select statement, it retrieves the records as instructed. Let's take another example, where first name equals John, a text value. All text values must be enclosed in a pair of single quotes. Once again, you just run the SQL select statement and it filters the required records. To specify your filter condition, you can make use of a wide range of operators. You've just reviewed an example of the equals operator and others you may have encountered in a previous lesson. Let's quickly review these other operators. SQL comparison operators include equal to, less than, and greater than. There's also less than or equal to, greater than or equal to, and not equal to. In addition to these symbols, the where clause can also use the between, like, and in operators. With the between operator, you can filter records within a specific numeric or time and date range. The like operator is used to specify a pattern in the where clause filter criteria. And the in operator is used to specify multiple possible values for a column. Now, let's explore some examples of the where clause in select statements. Recall the scenario of the admin department that wants to create reports for its engineering and science students. I can use the where clause to filter out the details of students who are in the engineering faculty. In this case, I need to retrieve all details, or all columns, from the student table. So I write select, asterisk, from, student table. Next I type where, followed by the filter criteria. The criteria is written as faculty, then an equal operator. Finally, I write engineering enclosed in single quotes, which are required for text values or operands. So I'm instructing MySQL to fetch only the details of the students who are attached to the engineering faculty. Then I run the query. As per the filter condition, it has retrieved the student records of the 3 students in the student table listed in the engineering faculty. Note that I could have used other operators such as greater than or equal to, greater than or equal to, and not equal, in the same way as the equal to operator in this where clause condition. You can use any of these operators with numeric values or operands. Now let's review some examples that use between, like, and in operators in the where clause condition. The college is a financial aid program available to students of a certain age. The funding department would like to notify eligible students only. I can use the between operator in the where clause condition to filter the records in the student table. As before, I type select, asterisk, from, student table, followed by where. After the where keyword, I specify the filter column as DOB or date of birth. Then I insert the between operator. Lastly, I give the date range as 1st of January 2010 and 30th of June 2010. Running this query retrieves the records of 4 students whose date of birth falls in the specified date range. Note that I could use any numeric range here, not just dates. For the next example, let's assume the admin department requires the details of the students who are in the science faculty. I can do this with the like operator, which can be used when you want to specify a pattern in the where clause filter criteria. Within the select statement, and after the where keyword, I type faculty for faculty column, then the like operator, followed by SC %, within single quotes. The percentage character in the pattern is a wildcard character that represents 0, 1, or multiple characters. The underscore sign can also be used to represent one single character. In this case, my where clause asks MySQL to search for and filter out values within the faculty column that start with SC, followed by any number of characters. So I run the statement and it filters out the 5 student records whose faculty column has a value of science. That is, starting with the pattern SC. In the final example, the admin department needs to know the details of the students who are studying in specific locations. You can use the in operator in the where condition to retrieve the relevant student records. Remember, the in operator is used to specify multiple possible values for a column. Within the select statement and following the where keyword, I type the column name, which is country, the in operator, then an open pair of parentheses. Within these, I place the values USA and UK each in single quotes. My select query will filter out all student records that have a value of USA or UK in the country column. Running this query returns 4 records, 2 students from the USA and 2 students from the UK. So the in operator searches for multiple possible values in the country column and filters out based on them. Note that although the examples in this video looked at the where clause in the select statement, it can also be used in other statements, such as update and delete. You've now learned what the where clause is, and you should now know how to use it to filter data as well as how to use different operators. Great work. Suppose you have a database that contains the records of college students from all over the world. As part of an annual report, a list of all the different countries these students belong to is required. It's very likely many students will come from the same country, so how can you retrieve the results you're looking for without any duplicates? Look no further than a select distinct clause. In the next few minutes, you'll learn how to describe the select distinct statement and explain what it's used for, demonstrate how to use it in a SQL query, and explain how it interacts with a single column, multiple columns, and null values in a few practical examples. Let's start by exploring what the select distinct statement is. In its most basic form, distinct, as its name states, returns only distinct or different values. In other words, it returns the results without any duplicates. Let's take a closer look at duplicate values. As you can imagine, columns in a table can often contain duplicate values. In a college's student records, for example, the country column will likely contain duplicate values as there can be many students who are from the same country. Let's assume you want to find out which countries the students in the college are from, so that you can get an understanding of which nationalities are represented in the college. You can begin by using a SQL select statement. You can write the select keyword, then country, followed by the from keyword and the student table name. Running this select query gives you 7 records as the result, with multiple duplicate records. In this case, there are duplicate records for Australia and the USA. So how can you eliminate these duplicates and retrieve a unique set of results? You can use the select distinct statement. You can write a select statement just like before, but this time add distinct after the word select. The word distinct will return all unique values in the table with no duplicates. You can then write the from keyword followed by the student table name. Once you run this statement, the countries now only appear once in the resulting records. All the duplicates have been removed. This is how the select distinct statement can be used to return distinct values from one column. In this case, you've returned distinct values from the country column. Now, let's take a few moments to explore the select distinct statement in action. The examples that follow focus on the select distinct statement with the use of multiple columns or when applied to a column that has a null value. With the student table in this example, I want to write a query to determine which countries are represented by students in different faculties. I can use a select distinct statement as before, but this time I'll add the word faculty before country. Running this statement produces 6 records. The science faculty has students from 3 different countries, as does the engineering faculty. So, with this statement which uses multiple columns, I've generated each unique faculty and country combination. Now, let's return to the table once more and examine how select distinct deals with null values in columns. In this example, I have a new student named Julia Smith from the USA. She's not yet been assigned a faculty or school address. As a result, both fields within these columns assigned to Julia Smith contain a value of null. So let's see what happens when I run the same select distinct statement as the previous example. How does it handle the null values? In other words, what results does it return for Julia? I select Go and receive the same result as the last time. But now there's also a record for Julia with a null faculty value and USA as the country. This is because the distinct clause considers null to be a unique value. So it outputs null and USA as a unique faculty and country combination. In this video, you learned how to use the select distinct statement to eliminate duplicate values in a select query result. You also observed how it behaves in response to values in a single column and multiple columns, and to null values in columns. Great work. You're at the end of SQL operators in sorting and filtering data. Well done. Having a lot of data stored in a database is great. Making sense of all that data is even better. That's why using SQL to manipulate the data becomes a much sought-after skill. You might remember that SQL operators can accomplish tasks such as arithmetic and comparisons. Data can be filtered using the where clause and sorted using the order by clause. Just to finish up, let's recap the key points of this module. Here at the end of this module, you should now be able to demonstrate the SQL arithmetic operators and tables, demonstrate the SQL comparison operators in a database, describe the purpose of an order by clause, and demonstrate ascending and descending sorts by single and multiple columns. In the videos on filtering, the where clause was used with the SQL select statement to filter records. For the where clause, you should now be able to explain the purpose of the where clause, describe how it is used to filter data, and demonstrate using the SQL where clause with comparison operators. Finally, you also explored the select distinct clause. Following this, you should now be able to explain the purpose of select distinct, describe how it is used to eliminate duplicate values, and demonstrate using select distinct with a single column, multiple columns, and null values. After this module, you should now be able to do some SQL operations on the data within your database. That's one of the first steps to giving real value to that data. With your SQL skills, the database is now no longer just a store. It's also something you can investigate and draw conclusions from. Before developing a database or a software application, you first need to plan how you'll organize your data. This plan is referred to as a schema. It's essentially a blueprint of what your data looks like. In this video, you'll learn how to explain the concept of a database schema, identify the different meanings of the term schema across different database systems, and outline the advantages of a database schema. Let's begin focusing on what developers mean when they use the term schema. The general meaning of a schema is that it's an organization or grouping of information and the relationships among them. In the context of a MySQL database, a schema means a collection of data structures or an abstract design of how data is stored in a database. Essentially, schema and database are interchangeable terms within MySQL. A schema is how data is organized in a database and how it's related to other data. But schema is defined in different ways across different database systems. In a SQL server, a database schema is a collection of different components like tables, fields, data types, and keys. In PostgreSQL, a database schema is a namespace with named database objects like views, indexes, and functions. And Oracle's schema system assigns a single schema to each user. Oracle even names each schema after its respective user. But no matter which type of database you encounter, the two most important concepts you need to understand when working with schemas remain the same: organization of data in the form of tables, and the relationships between the tables. Let's now cover the components of a database. A SQL Server schema is comprised of what are known as schema objects. Many of these objects will probably already be familiar to you from your study of databases. They include tables, columns, relationships, data types, and keys. An example of a SQL database schema is a music database with data on artists, albums, and genres all stored in separate tables. However, these tables can still be related to one another through various keys. In other words, the data within this database is organized in separate tables or entities. Yet the tables are also related to one another. Essentially, a database schema is comprised of all of the important data and their relationships, the unique keys for all entries in databases, and a name and data type for each column in a table. So, now that you're familiar with what a database is, let's move on and explore the advantages of a database schema. Schemas provide logical groupings for database objects. They also make it easier to access and manipulate these database objects than other available methods. Schemas also provide greater database security. You can grant permission to separate and protect database objects based on user access rights. And finally, it's possible to transfer ownership of schemas and their objects between users and other schemas. In this video, you've learned that a database schema is a structure that represents the storage of data in a database. You also now understand how the meaning of schema changes across different database systems. Lastly, you explored the advantages of a database schema.
By the end of this video, you'll know how to create a simple database schema using SQL. You'll do this by building the schema for a shopping cart database consisting of 3 tables. Let's start by creating a new database called Shopping Cart DB. First, I type the create database keyword followed by the name Shopping Cart DB. Then I run the statement. The Shopping Cart DB database appears in the left-hand explorer. Now I can create the tables inside this database. First, I need to create the customer table, which stores the following information on each customer: customer ID, name, address, email, and phone number. To create this table, I use the create table keyword, and then I type customer followed by parentheses. In the parentheses, I specify the fields and their data types as follows. The customer ID data type is integer, while the others are varchar. I give the name and email fields a character limit of 100. I assign a character limit of 255 for address, and I assign a limit of 10 characters for phone. Also note that I've used the primary key keyword on the customer ID column. This designates that field as the primary key of the table, a role you'll learn more about soon. Next is the product table, which stores the product ID, name, price, and description. I can specify this table as follows. The product ID has the integer data type. The name is a varchar with a 100 character limit. The price has a numeric type with parameters of 8 and 2. The description is varchar with a 255 character limit. And the product ID is set as the primary key within this table. And finally, there's the cart order table, which holds the order ID, customer ID, product ID, quantity, order date, and status. This table is set up as follows. The order ID, customer ID, product ID, and quantity are all integer types. Order date is date, and status is varchar with a 100 character limit. Order ID is the primary key here. However, this table also introduces something new in the form of two foreign keys. Before moving forward, let's quickly discuss what primary and foreign keys are. You may have noticed that the cart order table contains the customer ID and product ID fields. These same fields are also found in the other two tables. This is because these fields in the cart order table are directly linked to the same fields in the corresponding tables. To establish this relationship, each table must contain a primary key. The referencing table then uses foreign keys that point it to the external source table or the referenced table. You'll learn more about primary and foreign keys in greater detail in a later lesson. But for now, let's return to the shopping cart database example. All primary keys have been set up, so the foreign keys for the cart order table come next. I create the first one by using the foreign key keyword along with the customer ID column name. To link it to the customer ID field in the customer table, I then use the references keyword followed by the source table name customer and then customer ID in parentheses. Creating a foreign key for product ID is similar, but with product and product ID as references. So I use the foreign key keyword and name it product ID. I then reference it in the product source table product and then product ID. Then I execute these statements and the tables appear nested beneath Shopping Cart DB in the left-hand explorer. In this video, you learned the steps for creating a simple database schema using SQL. The same process applies for both small and large-scale databases.
When creating your databases, you need to be able to distinguish between different kinds of database schemas. In other words, you need to answer the question of what kind of database best suits my project. Over the next few minutes, you'll explore some different types of database schemas, and by the end of this video, you'll be able to explain the concept of a logical database schema and outline the concept of a physical database schema. Let's begin by exploring a logical database schema. A logical database schema is how the data is organized in terms of tables. In other words, it shows what tables should be in a database and explains how the attributes of different tables are linked together. Creating a logical database schema means illustrating relationships between components of your data. This is also called entity relationship, or EOR modeling. It specifies what the relationships between entity types are. Let's take the example of a simple EOR model that shows the logical schema of an ordering application. It demonstrates the relationship between an order, the shipment in which it will be shipped, and the courier assigned to it. The ID attribute in each table is the primary key of the respective entities. It provides a unique identifier for each entry, row, or record in the entities. In the order entity, the shipment ID and courier ID are called foreign keys, but in fact, they're also the primary keys of the shipment and courier entities, respectively. This creates a relation between these entities and the order table, which in turn has its own ID as its primary key. The other type of schema is physical schema. Physical schema is how data is stored on disk. In other words, this involves creating the actual structure of your database using code. In MySQL and other relational databases, developers use SQL to create the database, tables, and the other database objects. For example, you can create a physical schema for an online store database by writing SQL statements to create tables for customers, products, and transactions. However, physical schema creation could differ slightly between different database systems. Database schemas are vital when it comes to the creation of databases, and they form the basis of your application. You should also be able to describe how a logical database schema refers to the organization of data in tables, and that you use an EOR model to specify relationships between entities. And you should also now know that you can control how data is physically stored on disk by creating a physical schema with SQL statements. At this stage of the course, you spent some time exploring the relational model for databases. However, it's crucial that you have a proper understanding of how the relational model influences the design and structure of a database, and how it helps to build relationships between tables. Once you understand how your database is structured, Then you can determine how best to extract information from it. Over the next few minutes, you'll learn how to outline the basics of the relational model, identify the different relationships between tables, and explain the basics of an EOR diagram. To understand how the relational model influences our databases, let's take the examples of two tables from a college database. The first table shows a list of students, along with their assigned student and course identification numbers. And the second table lists courses that students can study, along with the ID for each course and its department. So the big question in this example is which student is studying what course? And is each student studying one or multiple courses? These are basic examples of why it's important to structure and connect tables correctly. There are three types of relationships between any two tables in a relational database: one-to-many, one-to-one, and many-to-many. Let's begin with an exploration of the one-to-many relationship. In a one-to-many relationship, a record of data in a row of one table is linked to multiple records in different rows of another. In the student table, a student with the ID of 1 is enrolled in 2 courses on the course table. So a one-to-many relationship can be drawn between these tables. This relationship can also be illustrated in a basic entity relationship diagram, or EORD, as student is enrolled in many courses, using shapes and symbols. The diagram depicts the two entities student and course in rectangle shapes with enrolled to describe the relationship in a diamond shape, and many is depicted using the crow's foot notation symbol. The relationship can also be illustrated using a more complex EOR diagram that depicts keys. Course ID in the student table is a foreign key, or FK, and this references the primary key, or PK, course ID column that exists in the course table. Next, let's take a look at one-to-one relationships. In one-to-one relationships, one single record of one table is associated with one single record of another table. To demonstrate this relationship, I'll use two new tables, one that outlines key information about the staff in each college department. The other is the department location table that records key data about the location of each department on campus. In this instance, each department head is in one department building on the college campus, so each staff member from the department staff table is associated with one record from the department table. These relationships can also be depicted in an EOR diagram as one department head leads one department. And finally, there's also many-to-many relationships. This type of relationship associates one record of one table with multiple records of another table. And the same relationship also works in the other direction. In this example, the student Morris Doyle is undertaking 2 research projects, and each project is supervised by a different staff member. And likewise, one staff member can supervise or collaborate with multiple students on their research projects. These relationships can also be depicted in an EOR diagram as many students are supervised by many staff. You should now be able to outline the different relationships that exist between tables in a relational database model. Good work. By now you're probably familiar with querying values or records within database tables. But how do you query specific records and values if they're duplicated across a table? When you come across obstacles like these, you can use keys as your solution. In this video, you'll learn how to explain the purpose of primary key in a database table and select a simple and composite primary key. You may have encountered several examples of primary keys during this course, and in these examples, you saw that they're used in tables as a unique method to identify a record and prevent duplicates. Let's take an example of a student table with 5 attributes: ID, name, date of birth, email, and grade. How could we identify a specific student to enter their grade? Like the student Mary on row 2. All you need to do is find the unique ID of Mary to identify a record of her data. However, in this example, you can't use the student name column because there are 2 students in a table called Mary, and you can't use the date of birth either because another student in a table called Dan has the same birthday. Neither of these records are unique to Mary, so what's the best approach? The solution is to locate a candidate key. This is an attribute that's unique to each row of the table, and it cannot have a null value. In other words, it cannot be empty. In this example, There are two possible candidate keys, the student ID and the student email. Both rows contain a unique value for each student, so either one can be used as the primary key. Let's assign the student ID as the primary key. Whichever column you reject as the primary key becomes the alternate or secondary key. In this instance, the email column is the secondary key. But what happens if you can't locate a unique value within a table? Maybe all rows have duplicated values. In this instance, you can create a composite primary key. This type of key is a combination of two or more attributes. Let's take the example of the delivery department of an online store. They have a delivery table that tracks the deliveries placed by their customers. However, there's no single column with unique values in each row. So, no column can be considered as the primary key. In this case, the best approach is to combine the customer ID and product code columns to create a unique value for each specific record of data. With these columns, you can determine which customer ordered what product. So together, these columns become the composite primary key. And this key can be used to track the delivery status for each customer. You're now familiar with one single column primary and composite primary key. You should now also be able to identify the most appropriate situation in which to use each one. Great work. Imagine a scenario where a bookstore has a database that contains two tables: customer table to track customer information and an order table to track customers' orders. But how can they determine which customer made which order? The solution is to add a customer ID column into the order table column as a foreign key. Over the next few minutes, you'll learn how to describe the purpose of a foreign key and demonstrate how to use it to connect different tables in a relational database. So what exactly is a foreign key? A foreign key is one or more columns used to connect two tables in order to create cross-referencing between them. By foreign, developers mean external. So the foreign key in one table will refer to an external or foreign column in another table. Let's find out more about how a foreign key works by exploring the tables from the database of an online store. The store's customer table contains information about the customer's name and address, while their order table contains information about each customer's order date and status. The issue is how to connect these tables to make sure that each order is associated with the right customer. Establishing this connection is important so that you can process and deliver orders to the right customers, update order details, or cancel orders if required. A foreign key is a great method of establishing a relationship between these tables so that these other tasks can be carried out. But before you learn about how to use a foreign key, let's take a few moments to explore the concept in a bit more detail. To find out more about how foreign keys work, let's take the example of the relationship between two generic entity tables. These tables are called Table 1, or T1, and Table 2, or T2. The purpose of connecting these tables is to relate records of data that exist in both tables with each other. The foreign key in T1 should point to a related column in T2. In this case, the foreign key column values in T1 must correspond to existing values in the referenced column in T2. And the reference column in T2 must contain unique values in each row of data. This will most likely be the primary column in T2. In addition, the reference table T2 is known as the parent table, while the referencing table T1 is the child table. Don't worry if all this seems a bit complicated. Let's simplify things by exploring an entity relationship diagram using the customer and order tables from earlier. In this diagram, the order table relates to the customer table by including the customer ID attribute and defining it as foreign key inside the order table. The relationship between these two tables is one-to-many. You might have encountered this type of relationship in an earlier video. One-to-many means that each customer may have many orders, but each order must refer to one single customer only. This means there must be a customer record available in the customer table before any order can be made. But it is not necessary to have an order once a new customer is created. Therefore, the customer table represents a parent table, and the order table represents a child table. This means that the parent can exist and the child may not exist, but the opposite scenario cannot occur. In this example, the customer ID value existing in the order table can be used to fetch the records of a specific customer to determine who placed the order. For example, to generate an invoice or to deliver an order to the customer address. It is also possible for a table to have more than one foreign key. Each will be used to connect the referencing or child table with other referenced or parent tables. In this case, you'll have multiple parents to the same child. Let's add a new table, product table, into the previous diagram to explain this in more detail. The order table now has two foreign keys. One foreign key links it with the customer table via the customer ID, and the other links it with the product table via the product ID. The relationship between these tables is one-to-one. Each order must be related to a specific product record, and each product might be related to an order record, but doesn't have to be. For example, you can receive a new product in your inventory, but no customer has placed an order on it yet. If an order has not been placed on this product, then it's not related to any order yet. So this then raises the question, who is the parent and who is the child? The customer, the order, or the product? The answer is that there are now two parents, the customer and the product tables, and there's one child, which is the order table. You should now understand the purpose of a foreign key, and you should also be able to demonstrate how it can be used to connect tables in a relational database. Well done. When building a database, there's often a lot of different tables that you'd need to consider including. But how do you determine what to include and what to exclude? The answer is to identify the entities you're interested in maintaining data on. In this video, you'll learn how to explain the meaning of entities in a relational database, differentiate between attribute types, and be able to identify entities and their attributes. So let's begin by exploring what an entity is. An entity can be described as an object that has properties which define its characteristics. An entity can be anything that represents a single object in a database, such as a place or a person. In a relational database system, each interesting object in a project could be considered an entity. For example, a customer or individual. And an entity in a table is comprised of rows and columns created in database management systems such as MySQL. Let's explore this concept in more depth using the example of a table that holds delivery records for the database of an e-commerce store. The table name represents the entity name, deliveries, and each column represents the entity-related attributes. And the system holds customer or entity-relevant attributes such as ID, name, and delivery status details. These attributes hold relevant data about the table entity. So, each instance of the customer entity in this e-commerce system contains a record of data about each customer. But there are also different types of attributes in a relational database system. These include simple attributes, composite attributes, and single-valued attributes. And there are also multi-valued attributes, derived attributes, and key attributes. Let's explore these attributes in more detail using the example of a student table in a relational database system. A simple attribute is an attribute that cannot be classified further. In the example of the student records, the grade values cannot be classified further. A composite attribute is an attribute that can be split into different components. For example, the name value of each student could be split into sub-attributes such as first and last name. A single value attribute can only store one value. In the student table example, the date of birth column can only contain one value per student. So these values could be defined as a single valued attribute. With a multi-valued attribute, the attribute can store multiple values in a field. For example, the student email column could hold more than one email per student, a college email address, and a personal email address. However, this practice should be avoided in a relational database. A derived attribute is where the value of one attribute is derived from another. In the student table, the age of each student can be derived from their respective date of births. And finally, there's the key attribute. This is a field that holds a unique value used to identify a unique entity record. A good example are the values contained in the student ID column. Each ID is a unique value which can be used to obtain data about a specific student. Remember that there's no point in considering entities or attributes that will not be used in your project. You only need to capture data in your database system that helps the users of your system complete certain tasks and activities. You should now understand the concept entities in a relational database and be able to differentiate between attribute types. Good work. At this stage, you might be familiar with the process for creating tables within a database. But there are several issues that you're likely to encounter when working with tables, such as unnecessary data duplication, issues with updating data, and the effort required to query data. Fortunately, these issues can be resolved with the use of database normalization. By the end of this video, you'll be able to explain what database normalization is, and you'll also be able to demonstrate an understanding of insert, update, and deletion anomalies, and be able to list some of the issues associated with them. Normalization is an important process used in database systems. It structures tables in a way that minimizes challenges by reducing data duplication, avoiding data modification implications, and helping to simplify data queries from the database. To gain a better understanding of normalization and the challenges it addresses, let's explore an example of a table that hasn't been normalized. In this example, I'll use a college enrollment table. The table serves multiple purposes by providing a list of the college students, courses, and departments, an outline of relationships or associations between students, courses, and departments, and name and contact details for the head of each department. Creating tables that serve multiple purposes causes serious challenges and problems for database systems. The most common of these challenges include insert anomaly, update anomaly, and deletion anomaly. Let's begin with an overview of insert anomaly. Insert anomaly occurs when new data is inserted into a table, which then requires the insertion of additional data. I'll use the college enrollment table to demonstrate an example. In the college enrollment table, the student ID column serves as the primary key. Each field in a primary key column must contain data before new records can be added to any other column in the table. For example, I can enter a new course name in the table, but I can't add any new records until I enroll new students. And I can't enroll new students without assigning each student an ID. The ID column can't contain empty fields. So I can't insert a new course unless I insert new student data. I've encountered the insert anomaly problem. An update anomaly occurs when you attempt to update a record in a table column only to discover that this results in further updates across the table. Let's return to the college enrollment table once again to understand how an update anomaly occurs. In the enrollment table, the course and department information is repeated or duplicated for each student on that course. This duplication increases database storage and makes it more difficult to maintain data changes. I'll demonstrate this with a scenario in which Dr. Jones, the director of the computing department, leaves his post and is replaced with another director. I now need to update all instances of Dr. Jones in the table with the new director's name. And I also need to update the records of every student enrolled in the department. This poses a major challenge because if I miss any students, then the table will contain inaccurate or inconsistent information. This is a prime example of the update anomaly problem. Updating data in one column requires updates in multiple others. Next, let's review the final challenge, deletion anomaly. A deletion anomaly is when the deletion of a record of data causes the deletion of more than one set of data required in the database. For example, Rose, the student assigned the ID of 4, has decided to leave her course. So I need to delete her data. But deleting Rose's data results in the loss of the records for the design department as they're dependent on Rose and her ID. This is an example of the deletion anomaly problem. Removing one instance of a record of data causes the deletion of other records. So how can you solve these problems? As you learned earlier, the answer lies in database normalization. Normalization optimizes the database design by creating a single purpose for each table. To normalize the college enrollment table, I need to redesign it. As you discovered earlier, the table's current design serves 3 different purposes. So the solution is to split the table in 3, essentially creating a single table for each purpose. This means that I now have a student table with information on each student, a course table that contains the records for each course, and a department table with information for each department. This separation of information helps to fix the anomaly challenges. It also makes it easier to write SQL queries in order to search for, sort, and analyze data. You should now be able to explain what database normalization is, and you should also be able to demonstrate an understanding of anomalies and challenges. Well done. As a database engineer, you'll very often come across columns in a table that are filled with duplicates of data and multiple values. This can make it quite challenging to view, search, and sort your data. But with the correct implementation of normalization, this challenge can be dealt with. By the end of this video, you'll be able to explain how to design a database in a second normal form, outlined the functional dependency concept, and defined the partial dependency concept. Before you begin, make sure that you've watched the video on first normal form, or 1NF. Database normalization is a progressive process, so you must be familiar with 1NF before you can implement 2NF. So why do database developers require database normalization? If you're going to store content, you should aim to have the best possible database. Best means that it has a proper structure that reduces duplication and ultimately allows for accurate data analysis and data retrieval. To get the best results, engineers build tables in a way that optimizes the database structure. This video focuses on how to design tables in a relational database to meet the second normal form criteria. But before you can learn how to do this, you need to understand what is meant by the terms functional and partial dependency. Functional dependency refers to the relationship between two attributes in a table. The unique value of a column in a relation determines the value of another column. To demonstrate this concept, let's take the example of a table known as R. This table contains two columns called X and Y respectively. X is a column with a set of unique values, which are not replicated elsewhere in the table, a primary key, for example. Y is a column without a set of unique values, like a non-primary key. R is the table or relation in which the columns X and Y exist. Y, as a non-primary key with duplicated values, is dependent on X. This is because X is the table's primary key, as it only contains unique values. Don't worry if you don't quite understand this concept yet. I'm going to demonstrate functional dependency in more detail. Let's take the example of a table called Student that holds key information on students in a college. The table contains three columns: a student ID column, a name column, and a date of birth column. I need to use this table to find the date of birth for a specific student. I can't use the name column because it has duplicated values. There are two students named Tony. If I query this column, I'll just receive both instances of Tony. And I can't use the date of birth column either, because there are two students who share the same date of birth. But I can complete this task by using the student ID column. All values in this column are unique, so it's designated as the table's primary key. And the values of this primary key column determine the information of the other columns. This means that each column in the table is functionally dependent on the student ID column. It's the only column that can be used to return specific data. Now that you've explored the concept of functional dependency, let's look at partial dependency. Partial dependency refers to tables with a composite primary key. This is a key that consists of a combination of two or more columns. To demonstrate, let's take the example of a table that shows the vaccination status of patients in a hospital database. The table shows the vaccination status of two patients, David and Kate. It also displays the patient ID, vaccine ID, and vaccine name. There's no one single column with unique values in each row, so there's no single column that can be used as a primary key. So it's best to combine both the patient ID and vaccine ID columns as a composite primary key to create a unique value in each record. The vaccination table must meet the second normal form, or 2NF. So all non-key attributes, the vaccine name, patient name, and status, must depend on the entire primary key value, which are patient ID and vaccine ID. It can't depend on just part of the value, otherwise this creates partial dependency. Let's apply this rule to find out if it's true for every non-key column. So, how do I check that the patient with the ID of 50 has taken vaccine 1? I check the value of both the patient ID and vaccine ID keys. The combined value is the only way to return the vaccination status value of a specific patient. This means that there's a functional dependency between the status value and the primary key value. But if I just want to find out the vaccine name, then I don't need both combined values. The only information I need to return the vaccine name is the vaccine ID. As you learned earlier, this is called partial dependency. This should be avoided in most instances as it violates the 2NF rule. Similarly, if I want to identify the patient's name, I don't need both combined values. I can just use the patient ID to return the patient's name. Next, let's look at how to upgrade this table to 2NF. First, I need to make all non-key columns dependent on all components of the primary key. So, I identify the entities included in the vaccination table. In this instance, there are three entities: vaccination status, as represented by the status column, vaccine, which is the vaccine ID and vaccine name columns, and patient, represented by the patient name and patient ID columns. I then break up the table into 3 separate tables as follows: patient table, vaccine table, and vaccination status. Now in each of these new tables, all non-primary key attributes depend only on the primary key value. I've eliminated all unnecessary replication of the vaccine and patient names within the vaccination table. The 3 tables are now in the second normal form, or 2NF. You should now be familiar with the 2NF rule and how to upgrade a table to 2NF. Good work. When working with tables in a database, you may often encounter tables that contain repetitive data. Perhaps 2 columns contain values that are very similar, so you might split the table in 2 to simplify the data. When building relational databases, you can solve similar issues of repetitive data using what's known as third normal form, or 3NF. By the end of this video, you'll be able to understand how to design a database in third normal form and explain the concept of transitive dependency. Before you begin, make sure that you've watched the videos in first and second normal form. A database must be in first and second normal form before it can be in third normal form. In addition to these rules, databases can't contain any instances of transitive dependency. In the context of third normal form, transitive dependency means that a non-key attribute cannot be functionally dependent on another non-key attribute. In other words, non-key attributes cannot depend upon one another. A key attribute in a database is an attribute that helps to uniquely identify a row of data in a table. To demonstrate this concept, let's take the example of a basic table with 3 columns, A, B, and C. The concept of transitive dependency means that the value of A determines the value of B. Likewise, the value of B determines the value of C. The relation between these table columns is represented by A, B, and C. This means that A determines C through B. This is the type of relation that database engineers call transitive dependency. Let's see how this works using a more complex example. I have a table of best-selling books within Europe from the database of an online bookstore. The table organizes the books according to 5 attributes: book ID and title, author name, author language, and country. In this table, ID is the only key or primary key that exists in the table. All other attributes are non-key attributes. But to determine what these non-key attributes are, I must use the ID of the top-selling books. This means if I want to find any specific information about any attribute, I need to use the ID attribute value to find the targeted attribute value. For example, if I use the ID of 3, then I can locate the author Cormac O'Dwyer, the language Irish, the country Ireland, and so on. However, it's also possible to determine the country based on the language, or to determine the language based on the country. And both country and language are non-key attributes. For example, in the context of Europe, it's always possible to determine the country is France if the language is French, and vice versa. This means that I have a transitive dependency in this relation. A non-key attribute depends on another non-key attribute. This dependency relation can be presented as follows. Language determines country, and country determines language. The rest of the attributes are fine, as they only depend on the ID primary key. So you can't say, for instance, that author name determines book title, or that author name determines language. For example, the author Michel Laurie has written 2 books in 2 different languages, French and Spanish. As I've just pointed out, the only transitive dependency that exists in this example is between language and country. So, how do I solve this transitive dependency within my table and remove any repetition of data? I can split the table into 2 tables while joining them to conform with 3NF rules. So, I keep the top books table while splitting off the country and language columns into a new table called country. But I also leave the country column inside the top books table as a foreign key that connects the 2 tables. The country table now holds just 4 records with no repetition of data. And there's no need for a language column within the top books table. Stating the country is enough to determine the language. And most importantly, all non-key attributes are determined only by the primary key in each table. This means that my table now meets the requirements of 3NF. You should now know how to design a database in third normal form, and you should also be able to explain the concept of transitive dependency. Well done. Well done. You've reached the end of this module on database design. It's now time to recap the key points and skills. You began this module with a lesson on designing a database schema and learned that a correctly designed database is the basis for all subsequent data storage and analysis. It's crucial to know the principles of good database design because a poorly designed database makes it hard, if not impossible, to produce accurate information. Having completed this module, you should now be able to define the term database schema, describe the schema of different database systems, create a basic database schema using SQL, and list the two main types of database schema. You then moved on to explore relational database design. In this lesson, you learned how to design a relational database. Having completed this lesson, you should now be able to describe the relational model, list different types of relations, evaluate an entity relationship diagram, or ERD, and explain the purpose of primary key in a database table. And you should now also be able to demonstrate how to select a single primary key and a composite primary key, describe the purpose of a foreign key, connect tables using a foreign key, and summarize the meaning of entities in a relational database. Furthermore, you should now be able to list different types of attributes, identify entities and their attributes, and create links between entities. The last lesson covered database normalization. Normalization is the process of converting a large table into multiple tables to reduce data redundancy. You should now be able to explain database normalization, recognize insert, update, and deletion anomalies, and explain the atomicity concept and describe the repeating groups of data problem. And you should now know how to design a database in first, second, and third normal form, and explain the concepts of functional, partial, and transitive dependency. You should now be familiar with the essential skills and concepts of database design, and you should also be able to create the structure of a normalized relational database. Well done. That's great progress towards your learning goals. In this course, you covered an introduction to database engineering. Let's take a few moments to briefly recap what you learned. In the opening module, you had an introduction to the course and explored possible career roles that you might want to follow. You also reviewed some tips around how to take this course successfully and discussed what it is that you hope to learn. You then covered an introduction to SQL, or Standard Query Language, the coding syntax used to interact with databases. And finally, you explored the basic structure of databases and learned about the different types of keys they use. You began Module 2 with an exploration of SQL data types and learned how to differentiate between numeric data, string data, and default values. You also completed several exercises in which you learned how to utilize these different data types in your database projects. You then moved on to explore CRUD, or create, read, update, and delete operations. You learned how to create databases and tables and populate them with data. You explored how to update and delete data, and you demonstrated your ability with CRUD operations by completing exercises in creating and managing data. In the third module, you reviewed SQL operators and learned how to sort and filter data. You began the module with a lesson on SQL operators in which you explored the syntax and process steps to deploy SQL arithmetic and comparison operators within a database. Next, you covered how to sort and filter data using clauses. The clauses that you learned about include the order by clause, the where clause, and the select distinct clause. You also covered an overview of how each clause is used to sort and filter data in a database. And you went through demonstrations of these clauses and had an opportunity to try them for yourself. In Module 4, you learned about database design. In the first lesson, you had an overview of how to design a database schema. You explored basic database design concepts like schema and learned about different types of schemas. The next lesson focused on relational database design. In this lesson, you investigated how to establish relationships between tables in a database using keys. You also learned about the different types of keys that are used in relational database design, such as primary, secondary, candidate, and foreign keys. Finally, you covered a lesson on database normalization. In this lesson, you investigated the key concepts around database normalization. You then learned about the concept of normal form and about the first, second, and third normal forms. Well done in completing this recap. Now it's time to try out what you've learned in the graded assessment. Good luck. Congratulations on reaching the end of this Introduction to Databases course. You've worked hard to get here and developed a lot of new skills during the course. You're off to a great start with your database learning, and you should now have a thorough understanding of databases and data. You were able to demonstrate some of this learning along with your practical database skill set by creating and querying a database in the project lab. Following your completion of this course, you should now be able to demonstrate knowledge of different database schema, explain relational database design and table normalization, perform database operations such as create, read, update, and delete, and demonstrate SQL commands by sorting and filtering data. In this course, you learned about databases. So, if you found this course helpful and want to discover more, then why not register for the next course? You'll continue to develop your skill set during each of the back-end developer courses. In the final lab, you'll apply everything you've learned to create your own fully functional database system. Whether you're just starting out as a technical professional, a student, or a business user, the course end projects prove your knowledge of the value and capabilities of database systems. The lab consolidates your abilities with the practical application of your skills. But the lab also has another important benefit. It means that you'll have a fully operational database that you can reference within your portfolio. This serves to demonstrate your skills to potential employers. And not only does it show employers that you are self-driven and innovative, but it also speaks volumes about you as an individual, as well as your newly obtained knowledge. You will soon receive your professional certificate in back-end development. The certification can also be used as a progression to other role-based certifications. Depending on your goals, you may choose to go deep with advanced role-based certifications, or take other fundamental courses once you earn this certification. Meta certifications provide globally recognized and industry-endorsed evidence of your technical skills. Thank you. It's been a pleasure to embark on this journey of discovery with you. Best of luck in the future.